James Webb looked back toward the universe's first dawn and found galaxies that shouldn't exist. Massive, structured, already ancient, appearing just a few 100 million years after the supposed beginning. So did Webb expose a crack in the Big Bang timeline, or are we misreading the oldest light in the cosmos? Every great scientific revolution begins the same way. An instrument performs flawlessly, and reality refuses to cooperate. In Webb's deep fields, the numbers look tidy, yet the implications feel almost impossible. To understand what's happening, we have to treat these images like evidence from a crime scene, beautiful, distant, and potentially misleading. Light crosses expanding space, gathers dust and noise, and arrives as a handful of infrared photons that must be translated into distance, mass, and age. That translation is where the stakes live. A single red smudge can become a galaxy at an extreme redshift, or a nearer object wearing a clever disguise. A slight tilt in a spectrum can mean primordial starlight, or a foreground contaminant, or emission lines bright enough to counterfeit a cosmic milestone. And yet, the tension is real enough to deserve a full audit. If some early galaxies are truly as massive and chemically developed as they appear, then our story of how structure forms, how dark matter scaffolds halos, how gas cools, how stars ignite, how dust and metals accumulate, may be missing something essential. But cosmology is not a single claim. It is a chain of linked measurements. The age of the universe is not guessed from one telescope's pictures, but inferred from relic light, elemental abundances, and the large-scale pattern of galaxies, each one a cross-check, each one a constraint. So when Webb's catalogue hints at systems that seem to mature too quickly, the question is not whether the universe has an older chapter hiding behind the first page. The question is whether we're reading the first pages correctly, and whether our cosmic clock is calibrated as tightly as we think. In this documentary, we will follow the photons all the way back to their origin, and forward through the pipeline that turns them into headlines. We will separate observation from inference, then test the three possibilities that matter: a measurement problem, a modelling problem, or a genuine mismatch between our standard timeline and the early universe's true behaviour. We will step inside Webb itself, where cold optics and a sunshield the size of a tennis court make infrared time travel possible. We will confront the redshift trap, where colour can masquerade as distance, and where assumptions about dust, starbursts, and black hole light can inflate a galaxy's apparent weight. And we will widen the lens beyond Webb, because this mystery does not live in isolation. It touches the Hubble tension, the growth of structure, and the uneasy fact that the universe's expansion history is both our ruler and our stopwatch. What emerges is neither an easy dismissal nor an instant overthrow. This is a high-stakes verification of the origin story we teach as settled. If the Big Bang framework holds, it will be because it survives the hardest kind of challenge, precise data that seems to point elsewhere, and if it bends, it will bend in a specific way, leaving fingerprints across the sky. Either outcome leads to the same destination, an account of the first luminous structures that is less comfortable, more exact, and far more interesting than we expected. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We begin with the unsettling claims, then rebuild the standard timeline, and finally interrogate every step from detector noise to cosmic history. By the end, you'll see how cosmology decides what to keep, what to revise, and what must be measured again. The claim lands like a warning, and it spreads with the speed of a headline. The James Webb Space Telescope has seen galaxies so distant, they appear to belong to the universe's first moments, yet some of them look too massive, too bright, and too chemically mature for that early time. On screen, the evidence is deceptively quiet. Pinpricks of light in a black field, surrounded by the soft grain of infrared noise. A few pixels brighten, a faint smear resolves, and suddenly the mind supplies a story. These are not just distant galaxies, they are ancient, and they are speaking from a time when the cosmos was still learning its own shape. Headlines compress it into a provocation, something older than the Big Bang. That phrase is not the literal allegation, and it cannot be, because time itself is part of the Big Bang story. The real issue is subtler and more dangerous for cosmology, because it hides inside our translations. The light suggests objects that seem older than the timeline allows. This documentary begins with that tension, not with a verdict, because the first chapter of any investigation is restraint. Webb has delivered candidate galaxies at extreme redshift, and the first analyses imply surprising stellar masses and rapid evolution. If those inferences hold, they strain the standard sequence of cosmic growth. If they fail, they teach us where our methods break and where our confidence was borrowed from assumptions. We need rules for the investigation. Astronomy is not prophecy, and it is not archaeology in the usual sense, where you can pick up a shard and date it directly. It is measurement through a moving medium where distance, time, and expansion are entangled. The question is not only what Webb saw, but what we think that light means. To look far away is to look back in time, and that is not metaphor but physics. Light travels at a finite speed, so every photon carries a timestamp embedded in its journey. A galaxy, 1 billion light-years away, is seen as it was 1 billion years ago. Push farther, and the look-back time approaches the universe's earliest eras, when stars were rare and the intergalactic gas was still mostly pristine. The effect is easy to say and hard to feel. In everyday life, light seems instant, and the world appears synchronized. In astronomy, the sky is a layered archive. Different distances mean different dates, all projected onto the same dome. When Webb stares into a deep field, it is not just collecting faint light, it is assembling a time sequence without ever moving. In the standard picture, the universe is about 13.8 billion years old. That number is not a guess pulled from one observation, and it is not a single ruler held up to the sky. It is a fit across many measurements, anchored by the cosmic microwave background and the expansion rate, with the physics of atoms and gravity tying the pieces together. When Webb sees a galaxy at extreme redshift, it is sampling a time when the universe was a fraction of its current age. That fraction matters because early time is not merely less time. Early time is a different physical environment, denser, hotter, and more rapidly changing. Matter was packed closer together, radiation fields were harsher, and small differences could amplify quickly. The timeline is therefore not just a calendar, it is a set of conditions that determine what kinds of galaxies can plausibly exist. The key term is redshift, and it is the first number everyone asks for. Light leaves a galaxy with a certain wavelength, set by atomic physics and by the stars that produced it. Hydrogen and oxygen imprint familiar lines, and whole populations of stars shape the overall colour. As that light crosses expanding space, the wavelength is stretched. The spectrum slides toward the red, and beyond red into infrared, where Webb is most at home. Higher redshift generally means earlier cosmic history. It is not a perfect clock, because the mapping depends on the expansion history of the universe and on the cosmological parameters we adopt. Still, within the standard model, redshift can be translated into distance and into cosmic time with calculable uncertainties. That translation is the backbone of every claim about the early universe, and it is where a small mistake can become a dramatic story. Redshift is often described like a Doppler effect, but cosmological redshift is different in origin. Doppler shift comes from motion through space, like a siren changing pitch as it passes. Cosmological redshift comes from space itself expanding while the light is in transit, so the wave is stretched between emission and detection. The galaxy can be nearly at rest in its local region and still be highly redshifted. This matters because our interpretation depends on the model of expansion, and the model is part of the claim. If the model is wrong, the inferred times can shift, and an apparent paradox can soften. If the model is right, then the redshift is a reliable signpost of youth, and the paradox sharpens. Either way, redshift is the first gate any anomaly must pass, because it sets the date on the cosmic postmark. Webb's role is not simply to see fainter dots, though it does that with astonishing ease. It is built to see the right wavelengths for the early universe, where the most diagnostic features have been shifted out of visible light. The first galaxies shine strongly in ultraviolet and visible light, powered by hot young stars that burn fast and blue. But by the time that light reaches us from extreme redshift, it has been stretched into the near and mid-infrared. Hubble could glimpse parts of this era, and its deep fields were a turning point in our sense of cosmic scale. Yet Hubble was not optimized for the deepest infrared, and it was limited by a warmer telescope environment and different detectors. Webb is colder, more sensitive, and tuned to longer wavelengths, with a sunshield that keeps its instruments in a steady, dark chill. That makes it a kind of time machine, not by bending time, but by catching ancient light that was previously invisible. Visually, the difference is almost like lifting a veil. A region of sky that looked nearly empty in older images fills with faint reddish sources in Webb's view. Some are nearby galaxies seen through dust, and some are far beyond them, dimmed by distance and stretched by expansion. The frontier is not a line. It is a gradient where interpretation becomes as important as detection. The unsettling part is what some of that light seems to imply. Several early Webb surveys reported candidate galaxies at redshifts around 10 and beyond. In the standard timeline, that corresponds to the first few 100 million years after the Big Bang, a period when the first sustained star formation is expected to ignite. In that narrow window, galaxies should still be building their first large reservoirs of stars, assembling inside young dark matter halos. Yet some candidates appear extraordinarily luminous, and the brightness is not a trivial detail. Luminosity can mean many things, including bursts of star formation, unusually low dust obscuration, or the presence of an active black hole. But when combined with colour and spectral shape, brightness can be converted into an estimate of stellar mass, because starlight follows patterns that population models can approximate. Some early estimates suggested masses comparable to mature galaxies, arriving far earlier than expected. Mass is not the only pressure point, because age in astronomy is often inferred indirectly. Chemical evolution is another, and it is tied to a simple origin story. The early universe begins with mostly hydrogen and helium, with only trace lithium produced in the first minutes. Heavier elements are forged in stars and spread by supernovae, and dust grains condense from those enriched outflows. So a galaxy that looks metal-rich at very high redshift implies multiple generations of stars and a rapid cycle of birth and death. There is a visual corollary to that chemistry. Metals and dust change how a galaxy looks, because they absorb ultraviolet light and re-emit energy at longer wavelengths. They also cool gas more efficiently, allowing it to collapse and form stars faster, which can accelerate growth once enrichment begins. The question becomes circular in a dangerous way. Does the galaxy look evolved because it is evolved, or because our models interpret its colours as maturity? Structure is the third pressure point, and it is where cosmology meets gravity. In lambda CDM, small fluctuations grow into larger ones through gravitational collapse, guided by dark matter that clumps without colliding. Galaxies assemble hierarchically, with smaller systems merging into larger ones, and with gas streaming along filaments of the cosmic web. There is room for fast growth, but there are limits set by available time and by the efficiency of turning gas into stars. So what does too early actually mean, when stripped of drama? It means a galaxy that seems to have accumulated too much stellar mass too quickly, given the time implied by its redshift. It means a galaxy that seems to have produced metals and dust before there was time for many stellar generations. It means a galaxy that looks settled when the universe should still be improvising, building the first stable patterns out of turbulence. These claims arrive with caveats that are easy to miss, especially when the images are beautiful. Many of the most dramatic objects began as photometric redshifts, inferred from broad colour filters rather than precise line measurements. That method is powerful for surveys because it can triage thousands of sources quickly. But it can be fooled by dust, by strong emission lines, and by lower redshift interlopers that mimic the same colour dropouts. Spectroscopic confirmation is harder, slower, and more decisive because it seeks specific fingerprints. A spectrum can reveal a sharp break where hydrogen absorption cuts off light, or it can show emission lines whose spacing gives an unambiguous redshift. But spectra require more observing time, and the faintest sources push instruments to their limits. In the early Webb era, the tension grew partly because the photometric candidates arrived faster than the confirmations. Even with the redshift pinned down, mass and age are model-dependent, and the models are not neutral. Astronomers infer stellar mass by fitting the observed spectrum to population synthesis models, which simulate how starlight evolves over time. Those models assume an initial mass function, star formation histories, dust attenuation, and metallicity, and each assumption carries a plausible range. Change those assumptions and the inferred mass can shift substantially, sometimes enough to dissolve an apparent crisis. Brightness can also be deceptive, because the universe contains natural magnifying glasses. A compact galaxy can appear brighter if it is gravitationally lensed by mass along the line of sight, and the lensing can be subtle enough to miss at first glance. A galaxy can look overgrown if an active nucleus contributes light that is misattributed to stars. Strong emission lines can inflate flux in certain filters and mimic older stellar populations, especially when the lines land inside a broad bandpass. Every anomaly must survive these alternative explanations, and that survival is a process rather than a moment. Pipelines are refined, calibrations improve, and independent teams reanalyze the same data with different priors. In astronomy, confidence is built by convergence, when different methods, different instruments, and different assumptions point to the same conclusion. Until then, the most responsible posture is curiosity under constraint. Still, the reason this story matters is that the tension is not trivial, and it did not come from a single sensational plot. Webb is not a single measurement, and the early results were not a single team. Multiple groups using different pipelines found candidates that pushed against expectations, and that repetition is what triggered attention. The community response was immediate, because the stakes touched the foundation of cosmic history. That foundation is the standard model of cosmology, often called lambda CDM, and it is both powerful and strangely minimal. It combines general relativity with a universe dominated by dark energy and cold dark matter, plus ordinary matter and radiation as smaller components. It explains the large-scale structure, the expansion history, and the pattern of the cosmic microwave background. It sets the timeline within which galaxies must form, and it sets statistical expectations for how many massive galaxies should exist at a given epoch. Historically, this framework was not born whole. The Big Bang picture matured through the 20th century, sharpened by the discovery of the cosmic microwave background in 1965, and refined by satellite missions that mapped it with increasing precision. Each improvement turned cosmology from philosophy into parameter estimation, where numbers could be tested and revised. Webb's tension matters because it targets that era of precision, where the uncertainties are supposed to be narrow. Inflation is part of the benchmark narrative, and it functions like an opening chapter we infer rather than observe directly. It is the leading idea for why the universe is so uniform on large scales, and why tiny quantum fluctuations became the seeds of galaxies. The cosmic microwave background preserves a snapshot of the universe when it was about 380,000 years old, when electrons and nuclei first combined and light could travel freely. From that snapshot, we infer the initial conditions for later structure formation, including the spectrum of primordial density ripples. Within this framework, the early universe is not empty, but it is constrained, and the constraints are physical. Gas must cool, collapse, and ignite stars, and cooling depends on composition and density. Feedback from radiation and supernovae can heat gas and drive winds, slowing further growth even as it enriches the surroundings. Dark matter halos must merge and deepen to hold onto gas against those outflows, and the balance between inflow and feedback sets the pace of assembly. The first few 100 million years are busy, but they are not infinitely flexible. If galaxies are too massive too early, the models must either increase star formation efficiency, change feedback strength, or alter the rate at which halos grow. Each adjustment has consequences elsewhere, because the same physics must also reproduce later galaxies in the observed cosmic web. That is why these early points of light can feel like pressure on an entire scaffold. So the mystery can be stated cleanly, without the noise of slogans. Webb appears to show galaxies that, if interpreted straightforwardly, formed stars faster and earlier than our models predict. That could mean the galaxies are mischaracterized, or the redshifts are wrong, or the masses are overestimated. It could also mean the astrophysics of early star formation is more efficient than we thought, perhaps because the first stars formed in denser gas than our simulations typically assume. And there is a deeper possibility, one that scientists treat with caution because it is tempting. If the expansion history is different, the mapping from redshift to time changes, and the same observed redshift could correspond to a slightly older universe. If dark matter behaves differently on small scales, early halos could grow faster and assemble stars sooner. If the initial conditions from inflation are modified, the first structures could be seeded earlier or more strongly, altering the expected abundance of massive galaxies. In the extreme, the anomaly could point to a crack in the story of origins, though cracks are rare and usually smaller than they first appear. Cosmology has seen apparent contradictions before, and many have resolved into better understanding of dust, selection effects, and calibration. The history of the field is a reminder that the universe is subtle, and our instruments are human-made. The question is not whether we can be surprised, but whether the surprise survives the next round of scrutiny. But extraordinary claims in cosmology usually shrink under scrutiny, and that is not cynicism. Better calibration can remove spurious brightness, and better background subtraction can change a flux measurement enough to alter a mass estimate. Better spectroscopy can demote a high redshift candidate to a nearer object, where its maturity is no longer paradoxical. Better modelling can reveal that a galaxy is young but dusty, not old and massive, and the difference can hinge on small changes in assumed stellar populations. The first job is to separate what Webb truly measured from what we inferred, because measurement and inference are stitched together in astronomy. Webb measures photons, their arrival rates, and their distribution across wavelengths. We infer distances, ages, and masses by placing those photons inside a theoretical map. When the map is wrong, the light can look impossible, even if the photons are perfectly real. This is the investigative tone we will keep because it matches how science actually moves. Anomalies are not embarrassments, and they are not trophies to display. They are stress tests for instruments, for analysis, and for theory, and they reveal weak joints that routine results never touch. Sometimes they dissolve into ordinary astrophysics. Sometimes they force new physics into the open. For now, we hold 3 competing explanations in view, and we resist choosing too early. It could be a measurement problem, where photometry, lensing, or contamination misleads us, and the candidates are not as distant as they seem. It could be a modelling problem, where our assumptions about stars, dust, and feedback fail in the early universe, and we are misreading youth as age. Or it could be a genuine tension with lambda CDM, requiring changes to the cosmic timeline or its ingredients. To judge which path is real, we need to know what the standard timeline actually says. We need to know what the Big Bang model claims and what it does not claim, because misunderstandings can masquerade as revolutions. We need to know how the age of the universe is inferred and where the uncertainties live, because every parameter has error bars with a history. Only then can we decide whether Webb found impossible light or simply unfamiliar light. So we step back before we go further, and we let the baseline story speak. We start with the standard narrative of cosmic history, from the first seconds to the first stars, and we keep an eye on which parts are measured and which are inferred. We trace how inflation, the microwave background, and expansion combine into a clock, one that can be tested, recalibrated, and if necessary, revised. Then we return to Webb's galaxies and ask whether they truly arrived too soon, or whether our expectations arrived too late. The Webb tension only matters if the baseline timeline is real, tight, and internally cross-checked against independent relics. Cosmology claims a specific sequence of eras, and each era leaves measurable traces, light, element ratios, and statistical patterns in matter. These traces are not poetic metaphors, they are physical records, preserved in spectra, maps, and number counts. On screen, that sequence often appears as a clean graphic, a line marching from beginning to today. Yet the real timeline is more like a chain under load. Each link holds only because the others pull in the same direction. If one link slips, the whole chain must be tested again, including the assumptions we rarely notice when the fit looks perfect. The phrase Big Bang is often misheard as an explosion in space, like a bomb going off in an empty room. The modern model describes the expansion of space itself, with matter and radiation carried along as distances stretch. That difference is not semantic. It changes what center, edge, and even before can mean. In a visual sense, imagine a grid drawn on rubber with galaxies painted on the intersections. The grid expands and the paint dots drift apart even though no dot is the center of the stretching. From any dot, every other dot recedes, and the pattern looks the same in all directions, at least on the larger scales. That large-scale sameness is called homogeneity and isotropy, and it is an empirical claim, not a philosophical preference. That distinction changes what beginning means in physics, because it's not a fireball at a center. It is a hot, dense state everywhere, with temperatures so high that familiar atoms could not exist. The early universe is not stuff flying outward through space, it is space-changing scale, while the stuff cools as it goes. Cooling here is not like a hot rock losing heat to air, but like radiation redshifting as wavelengths are stretched. When people say the universe began, they usually mean the earliest moment our equations can describe with confidence. Earlier than that, we may need new physics, or a better theory of gravity, because our current tools stop agreeing. The word began becomes a boundary in mathematics, not necessarily a literal first instant. It is a warning label on an extrapolation, telling us where tested theory gives way to conjecture. General relativity runs the expansion backward toward extreme density and temperature, and it does so with ruthless consistency. That backward extrapolation hits a limit, where quantum effects cannot be ignored, and space-time itself may behave differently. The singularity is often treated as a point in time, yet it is really a sign that the model has left its domain. In other words, it marks the edge of our map, not proof that the territory ends there. Historically, this picture did not arrive fully formed. In the 1920s, Edwin Hubble's galaxy distances and redshifts made expansion hard to avoid, while Georges Lemaitre argued that expansion implied a denser past. Those early debates were not just about data, but about interpretation, whether redshifts meant motion, tired light, or something stranger. Later, the 1965 discovery of the cosmic microwave background turned an abstract idea into a measured, glowing relic. It was a signal that could not be easily dismissed, because it looked like thermal radiation from a once-hot universe. Inflation is the leading proposal for what happened near that limit, and it is a proposal with a specific job. It adds a brief epoch of accelerated expansion before the hot Big Bang phase, setting initial conditions that would otherwise look unnaturally tuned. Inflation is not the Big Bang itself. It is a hypothesized prelude that makes the later story easier to reconcile. It is also a framework with many variants, which is why its broad predictions matter more than any single mechanism. In accessible terms, inflation says the universe grew enormously in a tiny fraction of a second, expanding by an enormous factor. Space itself expanded faster than light can cross it, without violating relativity, because relativity limits motion through space, not the growth of space. The result is that regions once in close contact can be flung far apart, while still sharing a common origin. That shared origin is what makes the later uniformity feel less like a miracle and more like a consequence. Inflation solves a practical puzzle about uniformity, sometimes called the horizon problem. Distant regions look nearly the same temperature, even though they seem too far apart to have equilibrated by ordinary light-speed communication. Without inflation, the early universe would need to start strangely uniform, and the model would have to accept that as a coincidence. With inflation, the uniformity is inherited from a smaller, causally connected patch that was stretched beyond the horizon. Inflation also addresses flatness, a geometric puzzle that hides inside the Friedmann equations. Rapid expansion drives the geometry toward near-perfect spatial flatness, much as a small patch of a balloon looks flatter as the balloon grows. That is why today's measured curvature parameter sits so close to zero, close enough to demand explanation. The remarkable part is not that curvature is small, but that it stayed small across immense changes in scale. Most importantly, inflation seeds structure, and it does so in a way that is both subtle and testable. Quantum fluctuations are stretched to cosmic scales, becoming slight density variations that gravity later amplifies over billions of years. In plain terms, microscopic randomness becomes macroscopic architecture. The same quantum uncertainty that makes particles jitter in a lab becomes the blueprint for clusters and voids. Those variations are not a storytelling device, and they are not optional decoration. They are encoded in a pattern we can still measure, long after the first atoms formed in the statistical texture of the cosmic microwave background. The universe remembers its earliest ripples, and it remembers them with numbers. The memory is faint, but it is coherent, like a whisper that still carries the shape of the original sentence. After inflation ends, the universe is filled with a hot plasma of particles and radiation, and the energy density is immense. It expands and cools, and its contents change as temperatures drop, crossing thresholds where different particles become stable or rare. In this era, time is often tracked by temperature, because temperature sets what reactions can proceed. The clock is chemical and nuclear, and it ticks in phase transitions. In the first fractions of a second, particle physics sets the inventory, and the details matter. Quarks bind into protons and neutrons as the universe cools through the quantum chromodynamics transition, while antimatter largely annihilates away. A tiny excess of matter remains, and that asymmetry becomes everything we will later call stars, planets, and people. The mystery is not that matter exists, but why the imbalance was so slight and yet so decisive. Neutrinos stream freely through space once they decouple, because they interact so weakly with other particles. They carry away energy and subtly affect the expansion rate, leaving fingerprints in later observables. We do not see the cosmic neutrino background directly, yet its influence is woven into the timeline. In parameter fits, it appears as an effective number of relativistic species, a quiet term with real leverage. Radiation dominates the energy budget early on, meaning photons and other relativistic particles control the expansion. The universe behaves like a pressure-supported fluid, where light and matter are tightly coupled through constant scattering. Pressure resists gravitational collapse, so structure growth is delayed even though the seeds already exist. In this phase, gravity is present, but it is negotiating with a medium that pushes back hard. As seconds become minutes, the temperature falls enough for nuclei to form, and the reactions become one-way streets. This is Big Bang nucleosynthesis, one of cosmology's earliest tests, and it happens when the universe is roughly the temperature of a star's core. It is a brief window because the density drops quickly as expansion continues. The universe gets too thin too fast for nuclear burning to keep up. BBN predicts a universe made mostly of hydrogen, with about a quarter of its mass in helium, and those numbers are remarkably robust. It also predicts trace deuterium and a small amount of lithium, produced through specific reaction chains that depend on timing. The key is that the universe cools so fast that nuclear reactions freeze out, locking in the ratios. Once the temperature falls below key thresholds, the reaction network effectively shuts down. These abundances are not adjustable decorations because the physics is simple and the parameters are few. They depend on the baryon density and the expansion rate during those first minutes, which sets how long reactions can run. Change the density, and you change how efficiently deuterium is burned into helium. Change the expansion rate, and you change how quickly the window closes. Measure primordial deuterium in ancient gas clouds, and you constrain the amount of ordinary matter with impressive precision. That number must also agree with the CMB, or the model breaks, because both probe the same baryon density in different ways. Deuterium is especially valuable because it is fragile. Stars destroy it rather than create it. When we find it in near-pristine gas, we're reading a leftover signature from the first few minutes. Lithium is a known tension point, and it is a useful reminder of how science behaves under stress. Observed lithium in old stars often comes in lower than basic BBN predictions, even after careful modelling of stellar atmospheres. Even within a strong framework, some details can resist clean explanation, hinting at astrophysical systematics or subtle physics. The lithium problem is not a collapse, but it is a persistent itch that refuses to go away. After nucleosynthesis, the universe keeps cooling for hundreds of thousands of years, and the scale factor grows by orders of magnitude. It remains an ionized plasma, opaque because free electrons scatter photons efficiently through Thomson scattering. Photons are trapped in a dense fog, bouncing endlessly, unable to travel in straight lines for long. In this era, the universe is a brilliant furnace, but it is also a sealed room. During this era, light cannot travel far without being deflected, so the universe is not transparent. The universe is not dark because there are no photons. It is bright but fogged, like sunlight inside a thick cloud bank. The glow is real, but it cannot yet form a clear image. If you could stand there, there would be no stars to see, only a uniform glare smeared by constant scattering. Gravity is already at work on the inflation-seeded ripples, pulling slightly denser regions inward. Dark matter begins clumping early, because it does not couple to radiation the way charged particles do, and it feels no photon pressure. It can start building potential wells while ordinary matter remains locked in the photon-baryon fluid. Those wells are shallow at first, but they are persistent, and persistence matters over cosmic time. This is where dark matter becomes more than a placeholder in an equation. It provides gravitational scaffolding that can grow even while ordinary matter is pressure-supported, setting the stage for later collapse. In simulations, these dark halos form a cosmic web, filaments and nodes that later guide gas into galaxies. Visually, it is like frost spreading across glass, branching and connecting until the whole surface has structure. As expansion continues, the temperature drops to a few thousand Kelvin, and the plasma crosses a critical threshold. Electrons can finally bind to protons, forming neutral hydrogen, because the average photon no longer has enough energy to keep atoms ionized. The universe undergoes a phase change in transparency. The physics is atomic, but the consequence is cosmic. The fog lifts. That transition is recombination. though it is not an instant, and the name can mislead. It is a gradual process governed by atomic physics, the expansion rate, and the fact that a small fraction of energetic photons can keep ionizing atoms. As neutral atoms form, the scattering rate plummets, and photons decouple from matter. Decoupling is the moment the universe becomes a place where light can travel freely for the first time. Those freed photons stream across the cosmos and cool with the expansion, their wavelengths stretched as space grows. Today we detect them as the cosmic microwave background, a nearly perfect blackbody spectrum at about 2.7 Kelvin. It is the afterglow of a universe that once glowed like a star. The spectrum is so close to perfect that even tiny deviations become clues, not noise. Visually, the CMB is often shown as a mottled oval map, a projection of the whole sky. The colours look dramatic, but the real variations are tiny, tens of microkelvin on top of a uniform background. That faint texture is the universe's earliest photograph, taken long before any galaxy lit up. It is a baby picture, but one taken with statistical instruments rather than a camera lens. The CMB is not just a uniform glow, it has tiny temperature anisotropies that map the early density field. Hotter and cooler spots correspond to slight over and under densities, and those densities later evolve into the large-scale structure we observe. The pattern is statistical, meaning its meaning is in the distribution, not in any single spot. The map is not a message in one pixel, but in the correlations between pixels. Those anisotropies form a power spectrum with peaks and troughs, and the peaks are not arbitrary. They arise from acoustic oscillations in the photon-baryon plasma, sound waves driven by the tug-of-war between gravity and radiation pressure. The peak positions and heights encode the universe's composition and geometry with surprising clarity. Each peak is a fossil of a vibration, frozen at the moment photons last scattered. Baryon density affects how strongly the plasma oscillated, because baryons add inertia to the fluid. More baryons change the relative heights of the acoustic peaks, leaving a quantitative fingerprint that can be read from the spectrum. In plain terms, heavier fluid sloshes differently than lighter fluid. That sloshing is not metaphorical, it is a calculable wave equation, solved across an expanding background. Dark matter fraction affects gravitational wells and the timing of oscillations, because dark matter deepens the potential without adding photon pressure. It shapes the peak pattern in a way that cannot be mimicked by baryons alone, which is why the CMB is such strong evidence for non-baryonic matter. The fit is not just qualitative, it is numerical and tight. Remove dark matter, and the peaks do not merely shift, they stop matching in multiple coupled ways. Curvature changes the apparent angular scale of the peaks, because it changes how we project physical sizes onto the sky. A flat universe puts the first peak at a specific multipole, and observations land close to that value within small uncertainties. This is one of the most striking moments in modern cosmology, geometry read from ancient light. It is also a reminder that the sky is a measuring instrument, if we learn how to read it. Dark energy barely matters at recombination, yet it matters for the distance to that surface, because it changes the later expansion history. Late-time acceleration changes how we translate angles into physical scales, subtly shifting parameter inferences. This is why early universe and late universe measurements are coupled. Even when the physics is separated by billions of years, the universe is one system, and its integrals remember the whole path. The Hubble constant enters through the expansion history, and it is more than a single number. It helps set the distance ladder inside the model, linking early universe physics to today's expansion rate through integrated geometry. When that linkage strains, as in the Hubble tension, it raises the same kind of question Webb now intensifies. Are we misreading a rung of the ladder, or is the ladder itself built on an incomplete blueprint? Put these ingredients together, and you get standard model cosmology, Lambda CDM, a compact framework with broad reach. Lambda represents dark energy, often modelled as a cosmological constant, and CDM represents cold dark matter, meaning slow-moving and collisionless. The name sounds simple, yet it stands on decades of data and careful statistical inference. It is also a model of averages, describing the universe statistically rather than tracking every galaxy's biography. Lambda CDM is not a single claim, but a compact set of parameters that can be fitted and tested. With a handful of numbers, it predicts many observables across cosmic time, from element abundances to galaxy clustering. Its power is that it is constrained from multiple directions, not protected by any one dataset. When the same parameters explain unrelated phenomena, confidence grows for reasons that are almost forensic. The CMB is the anchor because it is clean and early, and because the physics is well understood. It is a snapshot from about 380,000 years after the Hot Big Bang, long before galaxies existed, when the universe first became transparent. In that snapshot, we see both the initial conditions and the early dynamics. We also see the imprint of the sound horizon, a standard ruler set by pre-recombination physics. From that snapshot, we infer the initial conditions for structure formation, including the amplitude and tilt of the primordial fluctuation spectrum. We also infer the expansion history that connects then to now, because geometry links the sound horizon to the observed angular scale. The inference is indirect, yet it is constrained enough to be predictive. It is like reconstructing a crime scene from footprints, except the footprints cover the entire sky. The universe age estimate comes from that same fit, and it is a derived quantity, not a direct measurement. Given the measured parameters, the model yields about 13.8 billion years, often rounded to 14, because the uncertainty is small compared to the number. The age is an output of the expansion history, not an input. It is the time required for the model universe to expand from the hot, dense state to the present measured conditions. This age is not found by dating a single object, and it is not the age of the oldest star. It is derived by integrating the expansion rate over time, constrained by CMB geometry and matter content. In practice, the calculation is a controlled extrapolation from early conditions to the present. When independent clocks like stellar populations and globular clusters approach that number, the agreement becomes another crosscheck rather than a coincidence. In practice, cosmologists fit the CMB power spectrum to a parameter set, using likelihoods and careful treatment of instrumental noise. The best fit implies a specific timeline of radiation domination, matter domination, and late acceleration, each with characteristic effects on growth. The timeline is not merely a story, it is a quantitative history. Every parameter nudges multiple observables, which is why the fit is both powerful and unforgiving. Radiation domination ends when matter becomes the main driver of expansion, and the timing of that transition matters. That handoff sets when structures can grow efficiently, because gravity gains leverage when pressure no longer dominates. The universe becomes more hospitable to collapse, though it is still far from forming stars. Even then, growth is hierarchical, with small halos merging into larger ones along the web. Matter domination is when dark matter halos assemble rapidly across a range of masses, merging and accreting along filaments. Baryons fall into those halos after recombination, cooling and fragmenting into the first stars, though the details depend on chemistry and feedback. The first light is not a single moment. It is a dawn that spreads across the cosmic web. In visual terms, isolated sparks appear, then multiply until the darkness looks perforated. Cooling is not automatic, and that is part of the tension Webb probes. Primordial gas lacks heavy elements, so it radiates heat inefficiently, relying on molecular hydrogen and a limited set of pathways. That makes early star formation sensitive to environment, density, radiation fields, and the violent inflows that feed young halos. When we see a mature-looking galaxy early, we are implicitly claiming those bottlenecks were overcome quickly. Much later, dark energy begins to dominate the energy density, and the expansion begins to accelerate. It accelerates the expansion and slows the growth of new large-scale structure because gravity has less time to pull matter together. The cosmic web still exists, but its future growth is muted. The universe keeps expanding, yet the formation of new, massive structures becomes increasingly difficult. This three-act expansion history is why early anomalies matter, even when they seem confined to a narrow redshift range. Change the early growth rate, and you change the later universe in ways we can test, from lensing to clustering. The timeline is interlocked, so a disturbance in one era echoes into another. The question is always whether the echo matches what we already observe. The model's strength is also its vulnerability, because the parameters are tightly constrained by high-precision datasets. There is limited room to move without breaking other successes, and that is exactly what makes tensions informative. A tension is not a failure by itself. It is a signpost pointing to either systematics or new ingredients. The scientific instinct is to ask what would have to change, and what else would change with it. That tightness is what gives Webb's claims their charge, because they target the early assembly of galaxies. A galaxy that is too massive too early is not just an odd object, it is a stress test of the whole fit. It asks whether the scaffolding, the cooling, and the conversion of gas into stars can proceed fast enough. It also asks whether our interpretation of faint infrared light is more fragile than we want to admit. To see the pressure point translate redshift into time using lambda CDM, and the numbers become visceral. At redshift 10, the universe is only a few 100 million years old, a blink compared to its current age. The higher the redshift, the narrower the window for growth. In that compressed window, every assumption about efficiency becomes a lever. In that window, halos must grow, gas must cool, and stars must form in environments unlike the modern universe. Feedback from radiation and supernovae must not blow the fuel away too efficiently, or star formation will self-limit. The first galaxies are not gentle systems, they are turbulent, metal-poor and intensely irradiated. Their star formation may be bursty, with episodes that flare and fade, leaving confusing signatures in broadband light. If Webb finds large stellar masses at those redshifts, several assumptions get squeezed at once. Star formation efficiency may be higher than expected, meaning more of the available gas becomes stars quickly. Feedback may be weaker or delayed, allowing gas to keep collapsing before it is heated and expelled. Or the stellar populations may be younger and brighter than assumed, which would make the same light correspond to less mass. Dark matter halo growth may be faster than simulations predict, perhaps because small-scale power is slightly enhanced, or our mapping from light to mass may be biased by dust, emission lines, or active nuclei that masquerade as stellar light. Each explanation lives inside the existing framework, but each one has consequences. The consequences are not abstract, because they would affect counts, clustering, and the later evolution of galaxies. The mapping from observed light to inferred stellar mass is especially fragile early on, because we are interpreting limited information. We fit sparse photometry with population models, and small priors can shift results, especially when strong nebular emission contaminates broadband filters. A young, bursty galaxy can look deceptively massive if its light is interpreted as older starlight. Even the assumed initial mass function matters, because it sets how much mass hides behind a given luminosity. Spectroscopy can tighten the story, because it can separate continuum light from emission lines and confirm redshifts more cleanly. Yet spectra are expensive in telescope time, and early surveys often begin with photometric candidates. That is why the procedural chain matters: selection, redshift estimation, lensing corrections, and stellar population fits. At each step, small biases can compound, and the final mass can drift upward without anyone intending it. Even so, the baseline expectation is not arbitrary, and it is not just what simulations say. It comes from the same initial fluctuation spectrum that the CMB measures, evolved forward under gravity with well-tested physics. When we say too massive, we mean too massive given the measured initial conditions and the available time. That phrase is doing a lot of work because it ties distant galaxies to a map of the infant universe. If early galaxies are genuinely overabundant, it could imply stronger small-scale power, which would accelerate the formation of small halos. It could imply altered dark matter physics, changing how structure grows on early small scales. It could imply new early energy components that modify expansion, though any such change must remain subtle. The word subtle matters, because the CMB leaves little room for dramatic departures. Cosmologists treat such possibilities carefully because the CMB is already precise, and it leaves little room for improvisation. Any new ingredient must preserve the observed peak structure and the inferred distances, or it will immediately conflict with the anchor. The challenge is to relieve one tension without creating three more. That is why the most interesting proposals are constrained, technical, and often uncomfortable. This is why the phrase older than the Big Bang is misleading but emotionally accurate, and it spreads quickly. The claim is really that some objects look older than their allowed cosmic time, given the baseline expansion history. The drama comes from the implied impossibility, a mature-looking system in an infant universe. It forces a question that is both scientific and human. How much of what we think we see is inference, and how much is truly measured? The standard timeline is a chain of linked constraints, and it is built to be checked, not believed. Break one link and the whole chain must be rechecked, from inflationary seeds to late-time acceleration. That recheck is not a retreat, It is the method working as intended. In a field where we cannot rerun the universe, consistency across relics becomes our experimental control. We need rules for the investigation. We must separate what is measured directly from what is inferred through a model, because those are different kinds of statements. The data are photons and counts. The story is what we compute from them. If the story changes, we first ask whether the photons were misread, misclassified, or miscalibrated. Webb measures photons in the infrared, and it measures spectra when time allows, capturing features that shift with redshift. Redshift gives distance and look-back time only after we adopt an expansion history, because redshift is a ratio of wavelengths, not a clock. A redshift becomes a time only when it is placed on the model's timeline. That translation is usually safe, but it's never free of assumptions. The CMB gives that expansion history with remarkable precision, but it is not the only input we trust. BBN abundances, galaxy clustering, and supernova distances all cross-check it, each sensitive to different epochs and physics. Agreement across these methods is what turns a model into a baseline. When the agreement is broad, the baseline becomes a tool we can use to interrogate new data. When those cross-checks agree, Lambda CDM becomes a working baseline, not a belief, and that distinction matters. When they disagree, we look for systematics first, then for missing physics, because instruments and assumptions can mislead. The goal is not to protect a framework, but to understand what the universe is actually doing. Sometimes the universe is ordinary and our analysis is flawed, and sometimes the analysis is careful and the universe is stranger than expected. So Chapter 2 ends with a calibrated tension, not a collapse of the timeline. The timeline from fireball to first light is coherent, predictive, and constrained, and it has earned its authority through repeated tests. Yet its very precision means that surprises have leverage. A small discrepancy can matter because it has fewer places to hide. If Webb's early galaxies are real and massive, they must fit inside that narrow corridor of allowed histories. If they do not, the corridor itself may need rebuilding, or at least widening in a carefully measured way. The question is not whether the universe can surprise us, but where the surprise enters the chain. Is it in the early seeds, the growth, the astrophysics of starlight, or the geometry that turns redshift into time? Now that the baseline is set, we follow the photons Webb collects. We track how redshift is measured, how distances are inferred, and how early galaxy properties are extracted, because the tension lives in those steps. In the next chapter, the mystery becomes procedural, how a faint smear of infrared light becomes a claim about cosmic time. Now that the baseline timeline is set, we follow the photons Webb collects, because the anomaly lives inside our measurement chain. Each claim about an impossibly early galaxy begins as a handful of infrared counts, teased from darkness and turned into a story. Before there is a headline, there is a detector well filling with charge, one arrival at a time, until statistics become something we can argue about. Webb was built for the early universe's shifted light, not for prettier pictures, and that design choice is the entire plot. The first galaxies radiated strongly in ultraviolet and visible wavelengths, yet cosmic expansion stretched that light into the infrared by the time it reached us. What we call ancient is often just stretched, and the stretching is a physical record of the universe's growth. That stretching is redshift in its simplest physical sense. Space itself expands, and the wavelength expands with it. The same process also dims the light, because the photons are spread over a larger area and arrive more slowly. In practice, the universe charges an entry fee for distance. Your signal is weaker, your clock runs slower, and your spectrum is displaced into bands your eyes cannot see. So Webb's advantage is sensitivity to faint infrared flux, where first galaxies now appear as tiny reddish smudges. In practice, that means it can detect sources whose brightness would have been buried under noise for earlier observatories. The camera is not discovering brightness so much as rescuing it from the background, and that rescue depends on hardware choices made decades before launch. The primary mirror is segmented and enormous by space standards, a gold-coated mosaic that unfolds like a mechanical flower. Its area is the key, because a larger collecting surface intercepts more photons per second. In visual terms, it is a honeycomb of light-gathering tiles, each segment aligned until starlight snaps into focus like a tightened instrument string. More collected photons mean higher signal-to-noise on sources near the detection limit, where every count matters. When you are photon-starved, the statistics are unforgiving. Double the photons and you do not just see more, you trust more. The improvement is not cosmetic. It is the difference between a marginal detection and a measurement that survives reprocessing. Resolution matters for separating crowded objects, but faint high redshift work is fundamentally photon-limited. For the earliest galaxies, sensitivity often beats sharpness because the targets barely rise above the background glow. Even a perfectly sharp image cannot help if the object is too dim to register as anything but a fluctuation. In deep field images, the background is not empty and it is not quiet. There is zodiacal light from dust in our own solar system, diffuse emission from the Milky Way, and instrumental backgrounds that must be modelled rather than wished away. The scene looks like pure darkness, yet it is filled with faint gradients and soft glows that have to be subtracted with care. Webb also operates cold, because warm telescopes glow in infrared and drown the signal, like trying to hear a whisper beside a running engine. The physics is simple. Anything with temperature emits thermal radiation, and infrared detectors see that radiation as false sky. A telescope that is merely cool still shines at these wavelengths, and the detectors cannot tell the difference without calibration. A giant sunshield blocks sunlight, earthlight, and moonlight, and radiative cooling bleeds heat into space. Behind that shield, the observatory sits in a permanent twilight at the sun, Earth L2 point, where thermal conditions can be kept stable. The stability matters because drifting temperatures change detector behavior, tiny shifts that can masquerade as astrophysical signals. This cold environment is not a luxury. It is the difference between detection and self-inflicted noise. Infrared astronomy is always a fight against your own heat, and Webb was designed to win that fight by turning itself into a near-silent instrument. The quieter the telescope, the more confidently we can claim that a faint red smudge belongs to the universe, not to our machinery. The contrast with earlier missions is part of the historical context that makes Webb feel like a step change. Hubble transformed optical astronomy, and Spitzer opened the infrared sky, yet neither combined Webb's aperture with Webb's cold stability. Hubble could see deep, but it was looking in the wrong bands for the earliest ultraviolet light, while Spitzer looked in the right direction with a smaller mirror and blurrier vision. From this hardware comes the time machine effect, which is really wavelength access plus sensitivity rather than science fiction. Webb does not travel back in time, it intercepts light that has been stretched by expansion and delayed by distance. The farther the source, the longer the photons have been in flight, so every detection is also a message that endured the universe's entire history. The visual is deceptively calm, a dark field, a scatter of points, and then, after long exposure, faint galaxies bloom into view. But every pixel is a compromise between signal, background, and the telescope's own thermal and electronic behavior. The final image is a stack of many exposures, aligned and cleaned, where cosmic rays are removed and subtle detector artifacts are mapped like fingerprints. Catching ancient light is only the first step because interpretation sets the date. A galaxy becomes a crisis only after we translate colours into redshift, then redshift into time, and then time into a story about growth. The anomaly is therefore not just out there in the sky, it is also in here in the chain of inference. Webb's workflow starts with imaging that finds candidates, then spectroscopy that tests them, and the suspense lives in that gap. The first step can look decisive, because a dropout signature feels like a fingerprint, until the second step speaks. In that interval, the community is balancing excitement against caution, and both impulses are rational. NIRCam is the workhorse camera for near-infrared imaging and candidate selection, and it is built to do this triage quickly. It observes through multiple broad filters, building a low-resolution spectral fingerprint from colours rather than from lines. Each filter is like a wide window cut into the infrared, and the pattern of brightness across those windows becomes the first clue. In deep fields, NIRCam finds thousands of faint sources, then flags the reddest ones with automated selection cuts. Those red colours can mean extreme distance, or they can mean dust, lines, or both. And the ambiguity is the trap. The reddest objects are also often the faintest, so the same candidates that look most dramatic are also the ones with the loosest constraints. A deep field is also a visual lesson in statistics, because most objects are ordinary, and only a few are extraordinary. The rarest candidates sit at the edge of detectability, where the error bars are wide enough to hide alternative explanations. When you zoom in on a candidate, you are often staring at a handful of pixels, barely resolved, barely above the noise, yet heavy with cosmological meaning. NearSpec is the instrument for spectroscopy, where redshift can be measured line by line rather than inferred from broad colours. It can take spectra of many objects at once using microshutter arrays, tiny, controllable windows that select targets across the field. Visually, it is like placing a grid of miniature shutters over the sky, opening only the squares that contain your suspects. Even with that multiplexing, each spectrum still costs precious time, because faint galaxies require long integrations. The telescope must stare, steady and cold, while photons accumulate into a pattern that can survive calibration. The reward is a spectrum that can reveal whether a break is real or whether it was an illusion created by a single boosted band. MIRI extends Webb into mid-infrared, where warm dust glows and older stars contribute more strongly to the total light. MIRI can test whether a source is dust obscured or whether its energy distribution is dominated by mature populations. It also helps separate a genuinely distant galaxy from a nearer one whose dust has simply repainted its colours. The mid-infrared view changes the mood of the image because dust becomes a protagonist rather than a nuisance. In those wavelengths, star-forming regions can shine through their own soot, and a galaxy's apparent redness can be reinterpreted. The same object can look like a faint ember in NearCam and a warmer, broader glow in MIRI, two portraits that force different explanations. These instruments form a pipeline, and each step adds assumptions that can amplify if they are not challenged. Early headlines often skip the pipeline, but the pipeline is where the redshift trap is set, quietly, mathematically, and without malice. The trap is not a single mistake. It is the way uncertainties can align when the data are sparse. Redshift is a ratio, not a calendar, and it must be inferred from limited data before it can be translated into age. With imaging alone, astronomers often use photometric redshifts, which are powerful and fragile in the same breath. They are powerful because they scale to thousands of sources, and fragile because they compress a spectrum into a small set of numbers. Photometric redshift estimates come from comparing observed colours to template spectra, shifting those templates through redshift space. The method asks which redshifted template best matches the measured fluxes across the available filters. It is a competition among hypotheses, where the winner can change if one band shifts by a fraction of a microjansky. Under the hood, the algorithm is balancing competing fits, weighting each filter by its uncertainty and trying to avoid impossible spectra. In plain language, it is pattern matching with physics constraints, and it can be fooled when the patterns overlap. The overlap is worst when the signal is faint, because the likelihood surface becomes broad and multiple redshifts can look equally reasonable. At high redshift, one feature dominates the logic: the Lyman break in hydrogen absorption. Shortward of 1216 angstroms, intergalactic hydrogen absorbs strongly, cutting off ultraviolet light and carving a cliff into the spectrum. The cliff is steep because hydrogen is abundant, and because ultraviolet photons are exactly the ones it most efficiently blocks. That cliff is not merely a property of the galaxy, it is a property of the space between galaxies. Neutral hydrogen in the intergalactic medium acts like a fog for ultraviolet photons, and the fog thickens as we look deeper into the early universe. This is why the break is such a useful tool. Nature itself is drawing a boundary line across the spectrum. As redshift increases, that break slides into redder filters, creating a dropout signature that can be selected efficiently. A galaxy can vanish in bluer bands and reappear in redder ones, implying extreme distance if the break is real. The dropout technique is elegant because it turns the universe's absorption into a simple yes or no test across filters. This is the Lyman break technique, and it is the engine of many early claims because it scales well to massive imaging surveys. It works because the break is sharp and because Webb's near-infrared filters can bracket it cleanly. Historically, the same logic powered earlier dropout searches with Hubble, but Webb pushes the method into epochs Hubble could barely touch. Visually, the dropout looks like a ghost that refuses to appear in one set of images, then suddenly materializes in another. The temptation is to read that as a timestamp, as if the universe itself stamped a date onto the galaxy's light. But the ghost can be staged, and the stagecraft is ordinary astrophysics. But the dropout is not a unique fingerprint, it is a pattern that can be mimicked by other physics. Dust can redden a spectrum smoothly, making a lower redshift galaxy look like a high redshift dropout when the bluer flux is suppressed. If the bluest bands are shallow, dust can erase them below detection and create a convincing absence. Dust is not an abstract parameter. It is a population of grains, carbon-rich and silicate particles, formed in stellar winds and supernova ejecta. Those grains preferentially absorb and scatter short-wavelength light, reshaping a galaxy's colours in ways that can masquerade as distance. In the early universe, dust production is itself a puzzle, which means we're often modelling a moving target with imperfect priors. Strong emission lines can also distort broadband colours, especially in young starbursts packed with ionised gas. If a bright line lands inside one filter, it can inflate flux and create a false break between adjacent bands. The result is a spectrum that looks like it has a cliff, when it really has a spike. The most notorious culprits are nebular lines like O3 and H-alpha in star-forming galaxies, where hot stars excite surrounding gas. At certain redshifts, these lines fall into NIRCam bands and masquerade as continuum light, pushing the fit toward the wrong solution. A galaxy with extreme equivalent widths can therefore look older or farther than it truly is, simply because one band is being artificially brightened. In other words, a single narrow feature can hijack a broad measurement, because broadband filters integrate everything inside them. The camera does not know whether the photons came from stars or from glowing gas. It only counts them. This is why spectroscopy matters. It separates the smooth continuum from the sharp spikes, and it tells us what the camera had blended together. A photometric fit can then choose the wrong explanation, because multiple solutions match the same colours within the uncertainties. The algorithm may prefer a high redshift galaxy with a clean break over a dusty or line-dominated interloper, especially if the priors favour rarity. Priors are not cheating, they are assumptions about what is likely, and at the frontier our sense of likely is exactly what is being tested. This is the redshift trap, where limited filters and strong priors produce dramatic ages quickly. The trap is not fraud, it is an honest ambiguity that looks like certainty when compressed into a single headline number. The danger is psychological as much as technical. Our brains prefer a single answer, even when the data support a family of answers. The ambiguity grows when the data are near the noise floor, where small flux shifts matter more than our intuition expects. A slight change in background subtraction, or a small calibration update, can flip the preferred redshift and rewrite the implied cosmic time. Deep field reductions are therefore living documents, and the same image can subtly change as pipelines improve. Even the choice of templates matters, because templates encode assumptions about galaxies that may not hold at the dawn of structure. If early galaxies have unusual spectra, the template library can misclassify them by construction, accurate fits for the wrong reasons. A fit can be statistically good while being physically misleading, which is a quiet kind of failure. There is also a subtle selection effect that makes the trap more likely in exactly the places we look. Deep fields are designed to push to the faintest limits, and the faintest limits are where degeneracies multiply. When you deliberately hunt near the edge, you should expect a higher fraction of mirages, even when everyone is acting carefully. Photometric redshift is therefore a triage tool, not a verdict, especially at the frontier where the universe is least familiar. It tells us where to point spectroscopy, and it tells us where the story might break under closer inspection. The method is indispensable, but it is not the final court of appeal. Spectroscopic redshift is the attempt to replace pattern matching with direct identification of features. Instead of colours, we look for specific spectral lines whose rest wavelengths are known from laboratory physics. The laboratory anchor is important because it ties cosmic inference to measurements we can repeat on Earth. A spectrum spreads light into many wavelength bins, revealing breaks and emission features with far more precision than imaging. When a line is detected, the redshift is the observed wavelength divided by the rest wavelength minus 1, a simple equation with profound consequences. That equation turns a faint bump into a distance, and a distance into a position on the universe's timeline. For early galaxies, Lyman alpha is a tempting line, because it is strong in star-forming regions and sits near the Lyman break. Yet it is often suppressed by neutral hydrogen, and during reionization the intergalactic medium can absorb it before it reaches us. The line can also be scattered, reshaped or shifted by gas flows, so even when it appears it may not be a clean beacon. That suppression is itself a clue, because it ties galaxies to the state of the cosmos around them. If Lyman alpha is missing, it may not mean the galaxy is absent. It may mean the universe between us and the galaxy was still partly opaque. In that sense, the spectrum is not only about the galaxy, it is also about the fog it had to shine through. Other lines can be more robust in the rest optical, shifted into Webb's near-infrared at moderate to high redshift. Thus an H-beta and sometimes H-alpha can confirm redshift for somewhat later epochs, anchoring distance with a recognizable pattern. When multiple lines appear together, their spacing acts like a barcode, difficult to counterfeit by chance. The gold standard is multiple lines with consistent spacing, or a clear continuum break plus lines that agree. With that, the distance estimate stops being a guess among templates and becomes a measurement that can be cross-checked. Even then, the spectrum must be calibrated, sky-subtracted and interpreted, but the degrees of freedom shrink dramatically. Yet spectroscopy is observationally expensive, and that cost shapes the early narrative in ways viewers rarely see. Deep imaging can find candidates fast, while spectroscopy lags behind, and the gap invites premature certainty. The lag is not negligence. It is the reality of finite telescope time and the brutal faintness of the targets. There is a practical reason for that lag that feels almost cinematic. The telescope can photograph a crowd quickly, but it can interrogate only a few suspects at a time. The most dramatic suspects are often the faintest, and the faintest demand the longest interrogation. Sometimes the telescope returns with silence, and the silence itself becomes data that must be interpreted cautiously. When spectroscopy arrives, some candidates move, and the timeline moves with them, sometimes abruptly. A galaxy thought to be at redshift 15 can drop to redshift 5, and the crisis evaporates into a lesson about degeneracy. The demotion can feel deflating, yet it is also the system working, claims becoming sturdier by surviving harsher tests. But the opposite can also happen, because spectroscopy can confirm the extreme redshift that photometry suggested. Then the crisis becomes sharper, because the measurement chain has fewer escape routes and fewer places to hide systematic error. Confirmation does not end uncertainty, but it changes its character from maybe it's close to then how did it grow so fast? Redshift is still not time until we map it onto a cosmological model, and that mapping is another translation layer. Converting Z to look-back time depends on the expansion history and on parameters like H0 and omega matter, which set the universe's pace. The mapping also depends on dark energy's role at late times, which indirectly affects how we extrapolate the clock backward. Within lambda CDM, the mapping is precise enough to feel like a clock, but it is not absolute in a philosophical sense. Small parameter changes shift the inferred age of the universe at a given redshift by tens of millions of years, and those shifts matter near the beginning. When the total available time is only a few 100 million years, tens of millions are not rounding errors. At the highest redshifts, those shifts matter because the available time is already tiny, almost claustrophobic. Move the epoch by 100 million years, and you change what growth rates are required and what physical processes must be unusually efficient. The same galaxy can go from surprising to nearly impossible with a modest change in assumed timing. This is why the anomaly is not only about galaxies, it is about translation from observation to narrative. The same observed photons can imply different cosmic ages depending on the assumed expansion curve, and that curve is itself measured with uncertainty. The universe is telling us a story in infrared, but we still have to decide how to convert that story into dates. After redshift comes the second translation, from light to mass and age, and this is where early Webb claims became most provocative. Mass is inferred, not measured, and the inference rests on models that compress complex stellar physics into tractable parameters. We're not weighing galaxies on a scale, we're estimating their contents from how they shine. Astronomers use stellar population synthesis models to connect observed spectra to stellar content, essentially building a galaxy out of many idealized star clusters. These models add up starlight from stars of different masses and ages, evolving them over time with no nuclear lifetimes. They also incorporate stellar atmospheres, evolutionary tracks, and the way metals alter opacity, technical ingredients that ultimately decide how bright one solar mass looks. The models are powerful because they encode decades of stellar astrophysics, from the main sequence to red giants and beyond. Yet they are also simplified, because no model can capture every binary interaction, rotation effect, or stochastic burst in a tiny early galaxy. In the smallest systems, a few massive stars can dominate the light, and randomness becomes a physical parameter. To run the model, you must assume an initial mass function, which sets the ratio of low mass to high mass stars. A top-heavy IMF makes a galaxy brighter per unit mass, lowering inferred masses, while a bottom-heavy IMF does the opposite. This is one of the most consequential hidden knobs in the entire pipeline, because it changes the conversion between photons and kilograms. This assumption is not trivial, because the IMF is measured locally and then exported to the early universe by necessity. The question lingers: did the first generations of stars form with the same mass distribution, or did different conditions tilt the outcome? If gas was hotter, more turbulent, or less enriched, the balance of stellar masses could shift, and our familiar templates could become subtly wrong. You must also assume a star formation history, whether steady growth or short bursts that flare and fade. A recent burst can dominate the light, making a galaxy look massive if interpreted as older, smoother formation rather than a brief episode. The irony is that a galaxy can be intensely bright, and yet not very massive, if its light is being produced by a small number of young luminous stars. Metallicity matters because it changes stellar colours and lifetimes, and it changes nebular emission from surrounding gas. Early galaxies may be metal poor, but rapid enrichment from supernovae can complicate the fit in ways templates miss. Metal lines also affect cooling in gas clouds, which influences how efficiently stars form, linking chemistry to the very growth rates we are trying to explain. In visual terms, metallicity is a subtle tint in the spectrum, a shift in how blue or red the stellar light appears at fixed age. In physical terms, it is the record of previous generations, because metals are forged in stars and dispersed by explosions. Every metal-poor fit is therefore a claim about how many stellar lives have already ended. Dust attenuation matters because it reshapes the spectrum, especially in the ultraviolet where young stars shine brightest. Dust can hide star formation, redden colours, and mimic the appearance of older stellar populations if the model is not constrained. When dust is allowed to vary freely, it can trade places with age in the fit, and the galaxy's history becomes a negotiation between two different kinds of redness. Nebular emission is a special hazard for broadband fitting at high redshift, because it can dominate certain filters. Emission lines and nebular continuum can add flux that is misread as starlight from older stars, inflating the inferred mass-to-light ratio. The nebula is essentially borrowing the star's energy and re-radiating it in discrete colours, and broadband photometry can mistake that borrowed light for extra stars. If that contamination is not modelled correctly, the inferred stellar mass can inflate dramatically, sometimes by factors that change the entire interpretation. The galaxy then appears too massive, not because it is, but because lines are counted as stars in the bookkeeping. This is one reason early reanalyses often focused on adding stronger nebular components and re-evaluating which bands were line-dominated. This is where the too massive problem first took shape in early Webb analyses, and why it felt like a challenge to the standard timeline. Some candidates, based on photometry, seem to have stellar masses comparable to later, mature galaxies, despite existing in the universe's first few 100 million years. The images looked like glimpses of adolescence, yet the inferred masses sounded like adulthood. In the standard timeline, those masses would require extreme star formation efficiency very early, converting gas into stars with minimal delay. They would also require rapid halo growth, and a feedback story that does not shut the process down, even as supernovae and radiation push back. The early universe is not gentle, and the same processes that create stars also tend to disrupt the gas that feeds them. The tension is easy to state and hard to resolve. How do you build so much stellar mass so quickly, without breaking other constraints? If the galaxies are real, either the early universe was more productive than we thought, or our inferences are biased upward. And if the inferences are biased, the bias must be identified, because it will affect everything else we measure at the frontier. But systematics can push masses upward in several mundane ways, and they can stack in the same direction. Overestimated redshift increases luminosity distance, which increases inferred luminosity, which increases inferred mass when the model tries to match the brightness. A small redshift error is not a small mass error, because distance enters the calculation with leverage. Emission line contamination increases flux in key bands, which increases inferred continuum level and can force older solutions. Dust assumptions can force the model toward older ages, which increases mass-to-light ratios, making the galaxy heavier in the model than in reality. When several uncertainties all prefer older and brighter, the fit can drift toward a galaxy that sounds implausibly mature. Gravitational lensing can quietly magnify a source, making it appear intrinsically brighter than it is. If the lensing is missed or underestimated, the galaxy is assigned too much intrinsic luminosity and mass, and the error can look like early maturity. Lensing is especially treacherous because it is a real astrophysical effect, not an instrument flaw, and it can hide in plain sight. The lensing can be subtle, especially when the foreground structure is faint or when the magnification is modest. A slight stretch in the image, a mild arc, or a nearby foreground galaxy can be easy to overlook in crowded deep fields. Sometimes the only hint is statistical, an unusual concentration of bright candidates near a foreground overdensity. Active galactic nuclei can also contribute light, especially in compact bright sources that look unusually concentrated. If an accreting black hole adds continuum emission, stellar mass can be overestimated by fitting it as starlight, because the model assumes stars produce the photons. The irony is that a small black hole feeding efficiently can impersonate a much larger stellar population. Each effect alone may be modest, but together they can create an illusion of maturity that feels decisive. The redshift trap is therefore not only about distance, it is about compounding inference, small biases that multiply into big conclusions. The deeper we push, the more we are forced to treat every step as a potential amplifier. The community response was to push candidates through stricter tests, especially spectroscopy and improved modelling of nebular emission. Some dramatic objects were demoted to lower redshift and their masses fell into ordinary ranges, dissolving the initial shock. The story here is not embarrassment, it is refinement, the slow tightening of a measurement until it either holds or breaks. Those demotions did not end the story, because not every candidate moved when the analysis tightened. A subset remained extreme even after improved modelling, deeper imaging, or partial spectroscopic constraints, and that persistence is what keeps the mystery alive. When an object survives multiple attempts to explain it away, it stops being a curiosity and becomes a pressure test for the whole framework. This is the tension at the heart of the chapter, because it resists a single clean dismissal. The data do not yield one verdict. They yield a split outcome that demands patience, better spectra, and careful accounting of uncertainties. The split is uncomfortable, because it means the universe is not giving us a simple answer on schedule. In this split, we learn what Webb is really doing to cosmology, which is forcing an audit of our methods. It is not only finding early galaxies, it is exposing where our procedures are brittle and where our confidence outruns our constraints. In a sense, Webb is measuring us as much as it is measuring the sky, testing how we handle ambiguity when the stakes are high. The audit begins with humility about what imaging can and cannot prove, even when the images feel definitive. Photometry can suggest, rank and prioritize, but it can also seduce us with false precision, because the colours are few and the interpretations are many. When a candidate is defined by absence in one band, we have to ask whether we truly saw nothing, or whether we simply lacked depth. The audit continues with realism about spectroscopy, which is decisive but limited by time and scheduling. A gold standard that is too expensive becomes a bottleneck, and bottlenecks shape narratives by delaying the moment when ambiguity collapses. The public sees discovery, but the field sees a queue, targets waiting for their turn at the spectroscopic microphone. Then comes the hardest part, the modelling layer that turns spectra into physical histories, and this is where expertise becomes judgment. Stellar population fits are not direct readings. They are negotiated compromises between data and priors, tuned to match what we think galaxies can be. Two teams can use the same photometry, choose slightly different assumptions, and end up with different masses that both look reasonable on paper. In the early universe, priors are especially dangerous, because we have fewer anchor points and fewer nearby analogues. If early galaxies differ from local ones, our templates may be accurate only by accident, and our best fits may be the wrong story told smoothly. The question becomes unsettling. Are we learning about the early universe, or are we learning about the limits of our own libraries? So the redshift trap is not a scandal. It is a structural risk at the frontier of observation. It is the risk that our first interpretations will be overconfident, because the data are sparse and the stakes are high, and because humans crave coherent timelines. The trap is also a reminder that astronomy is indirect, built on inference, and therefore always vulnerable to elegant mistakes. Yet the trap does not mean the anomaly is false. It means it must be earned through repeated attempts to break it. The most interesting candidates are those that survive multiple reanalyses and still look too early, too bright, or too massive for comfort. Survival is not proof, but it is a reason to keep spending time, and time is the most precious currency in this business. In that survival, the central question returns with sharper edges, and it becomes harder to dismiss as mere confusion. Are we seeing genuinely rapid galaxy assembly, or are we watching our inference machinery overreach in a regime where it has never been stress tested? And if the early universe really did build quickly, what does that imply about how gas cooled, fragmented, and resisted feedback in the first halos? A tiny shift in interpretation can move a galaxy across the cosmic calendar, and the calendar is tight near the beginning. Change the redshift by 1 or 2, and you can add or remove hundreds of millions of years, which is an eternity at those epochs. In that compressed era, a little earlier, is not a small claim. It is a different universe. Change the mass-to-light ratio by a factor of 2, and the implied growth rate changes radically, from plausible to alarming. The crisis can become a cautionary tale, or the caution can become a deeper crisis, depending on which uncertainties collapse first. This is why the chapter feels like suspense. The same faint photons can support competing narratives until the next piece of evidence arrives. This is why Chapter 3 is procedural suspense, not just instrument admiration, and not just a parade of technical terms. Webb's power is real, but its discoveries are filtered through choices that can mislead, and through models that must be interrogated as carefully as the sky. The mystery is not only what Webb sees, but how we decide what Webb has seen. We now have the tools and the pitfalls on the table, and we can confront the anomaly itself. Next, we track what Webb actually saw in the deep fields, and which explanation survived first contact with data. The anomaly is now specific enough to measure, and specific enough to argue over. In Webb deep fields, some high redshift galaxy candidates look unexpectedly bright for their inferred distance, bright enough to stand out even in crowded infrared mosaics. When that brightness is translated into stellar mass, several objects land uncomfortably high, uncomfortably early, and the discomfort is mathematical rather than emotional. The tension is not aesthetic, it is arithmetic, because light becomes mass only through assumptions that can be tested. On screen, the deep field looks like a snowfall of faint embers, with a few points burning hotter than the rest. The background is not empty black, but a textured darkness, subtle gradients, diffraction spikes, and the faint haze of unresolved sources. Each bright speck is not just a dot, but a spectrum stretched by expansion and filtered by cosmic time. Webb's sensitivity in the near and mid-infrared lets it see rest frame ultraviolet and optical light from the early universe. That is the light most closely tied to young stars, ionized gas, and the first heavy elements. The camera lingers on a single candidate, circled in a thin white ring, while false color filters translate wavelengths into blues, greens, and reds. Those colors are not paint. They are measurements of flux through carefully designed band passes. A galaxy that drops out in one filter and reappears in redder ones hints at a break in its spectrum. That break is often interpreted as the Lyman break, where neutral hydrogen absorbs photons shortward of 12^16 angstroms, yet the same pattern can be mimicked by dust, or by strong emission lines, or by a lower redshift galaxy with a different spectral discontinuity. In lambda CDM, redshift is a tight clock once the expansion history is chosen. The mapping is set by cosmological parameters, Hubble's constant matter density and dark energy density, which together determine how quickly the scale factor grows. At Z around 10 to 15, the universe is only a few 100 million years old, depending on the exact parameters and their uncertainties. That window is not just short, it is crowded with required steps. The model does not merely say early, it assigns a specific age to each redshift, and that assignment is what makes the anomaly measurable. A timeline graphic makes the pressure obvious, because the first billion years are compressed into a thin strip. The difference between Z10 and Z15 is not a gentle slide. It is a steep drop in available time, like losing entire chapters of a story between adjacent ticks. In that interval, matter has only recently decoupled from radiation, and the first nonlinear structures are still assembling. If a galaxy already looks mature there, it is asking for a rapid sequence of events that must all happen quickly. a galaxy must first have a dark matter halo massive enough to hold gas against pressure and heating. The halo grows by gravitational collapse and mergers, guided by the initial fluctuation spectrum imprinted in the early universe. Those fluctuations are measured in the CMB as tiny temperature variations, and they seed where halos can form. In the standard picture, small halos appear first, then merge and accrete into larger ones. The earliest halos are not smooth spheres, but triaxial knots in a cosmic web, fed by filaments that funnel matter inward. The physics of collapse is simple in outline and brutal in detail. Dark matter, effectively collisionless, can pile up without radiating energy, forming a potential well that deepens as it accretes. Baryonic gas, by contrast, shocks and heats as it falls in, and that heat must be shed before the gas can condense. The virial temperature of a halo sets the regime because it determines which cooling channels are available. Below about 10,000 Kelvin, atomic hydrogen cooling becomes inefficient, and molecular hydrogen often carries the burden. Gas then falls in, cools, fragments, and forms stars that light up. Cooling is not a vague concept here. It is the process by which gas sheds energy through radiation, so gravity can compress it further. In metal-rich gas, atoms and ions provide many emission lines that carry energy away efficiently. In pristine gas, the cooling channels are fewer, and the temperature floor can stay higher. Molecular hydrogen can cool gas to a few hundred Kelvin, but it is fragile, and ultraviolet photons can dissociate it through the Lyman-Werner bands. Those steps are not optional, and each has a timescale that can bottleneck growth. Cooling is slower in pristine gas because metals are missing, and because molecular hydrogen can be fragile in strong ultraviolet fields. Feedback can eject gas and pause star formation, especially in shallow early halos. Even when gas remains bound, turbulence and heating can delay the collapse of dense cores. The early universe is denser, which shortens freefall times, yet it is also more violent, which can keep gas stirred and puffy. So what does it mean when a galaxy looks evolved at extreme redshift? It means the inferred stellar mass is high relative to the cosmic time available. It means the star formation rate is intense, or sustained enough to build that mass quickly. It also means the galaxy's light suggests a history, and that history must fit into a narrow slice of cosmic time. The word evolved sounds qualitative, but in practice it is a bundle of quantitative inferences. It can also mean the stellar population appears older than expected at that redshift. That phrase is often compressed into older than the Big Bang, which is shorthand and not literal. The real claim is older than expected given the model time assigned to that redshift. In other words, the fit is trying to place long-lived stars into an era that may not have had time to make them. The drama comes from the mismatch between the inferred stellar ages and the cosmological clock. The age estimate comes from fitting spectral energy distributions, usually with limited bands. A red continuum can indicate older stars or dust, or strong nebular emission, and those options can mimic one another in broadband photometry. The fit chooses among these, and the choice changes the implied history. A small change in assumed dust attenuation, or in the strength of emission lines, can swing the inferred age and mass. Even the assumed metallicity matters, because metal-poor stars are bluer at fixed age, shifting the inferred balance between youth and dust. This is where the visuals matter, because the data are often a handful of coloured points with error bars. The human eye wants to see a smooth curve, but the curve is a model family, not a direct measurement. Different star formation histories can produce similar colours once redshift and dust are allowed to vary. The anomaly lives in that ambiguity, because the same photometry can support competing narratives. A rising star formation history can mimic a younger population, while a declining one can mimic an older, redder mix. On screen, the SED fit appears as a ribbon of possible curves, with one best fit line drawn boldly through the points. The ribbon is the uncertainty space, priors, degeneracies, and the limited leverage of broadband filters. A single filter can be dominated by a strong emission line, turning what looks like continuum into line-boosted brightness. At these redshifts, lines like OTH and H-beta can slide into infrared bands, and their contribution can be large. If that line contribution is misestimated, the inferred stellar mass can inflate, because the model attributes line light to starlight. Evolved can also mean chemically enriched, which is a different kind of clock. Metals are forged in stars and spread by winds and supernovae, and their presence changes both physics and appearance. Metal lines cool gas more efficiently, and metal-rich stars have different spectra than metal-poor ones. If metallicity and dust are already significant, multiple stellar generations may have already lived and died. In the early universe, enrichment is not just chemistry, it is a record of how many times gas has been processed through stars. That compresses the timeline because enrichment requires both star formation and time for massive stars to explode. The first enrichment can happen quickly because the most massive stars die in a few million years, yet significant enrichment implies repetition, because one burst does not enrich all gas uniformly. It also requires retention, because early feedback can blow enriched gas away. The metal budget is therefore a constraint on both star formation intensity and gravitational depth. A galaxy that keeps its metals early is a galaxy that must be unusually deep or unusually lucky. Deep means a halo with a gravitational potential well strong enough to hold onto hot gas and fast winds. Lucky means the geometry and timing of outflows allow some enriched material to fall back. In simulations, metal retention is sensitive to halo mass, star formation clustering, and the surrounding environment. A dense filament feeding the galaxy can also help, because inflows can replenish gas even as outflows try to evacuate it. Dust adds another layer of tension, because dust is both evidence and a source of confusion. Dust can only form after stars create heavy elements, then condense grains efficiently in ejecta or in dense interstellar clouds. Yet dust also hides ultraviolet light and reshapes colours, which can bias mass and age upward. A dusty young galaxy can masquerade as an older, more massive one when only a few bands are available. The dust law itself is uncertain, because early dust grain sizes and compositions may differ from those in the Milky Way. On screen, dust is invisible, yet its fingerprints are everywhere in the colours. A galaxy that should glow blue with hot young stars can look muted and red, as if its light has passed through smoke. The narrator's challenge is to remind us that red does not automatically mean old. In the early universe, red can be the colour of obscured star formation. It can also be the colour of a spectral break misread as distance. The mystery deepens because each explanation collides with another constraint. If the galaxies are truly massive, their halos must be rare and fast-growing. If they are common, the number density becomes hard to reconcile with simulations. The tension is not only about one object's properties, but about how many such objects appear in a given patch of sky. A deep field is small, yet it samples a long cylinder of cosmic volume, and that geometry makes number counts meaningful. Number density is the quiet killer of easy stories. One extreme object can be a statistical fluke or a lensing accident. A population of bright objects implies a shift in typical growth, not just an outlier. In hierarchical models, rare peaks exist, but their abundance is predicted by the halo mass function. That function falls steeply at high mass, and at early times it falls even more steeply, making the bright end exquisitely sensitive. Counts from early Webb fields suggested more bright high redshift candidates than many models predicted. The exact tension depends on selection, completeness, and contamination, which are technical words for how you find things and how many you miss. Completeness is about what the survey fails to detect, and contamination is about what sneaks in under the same colour criteria. Yet the basic question remains, how many such galaxies can exist without breaking the growth budget? If the bright tail is too full too soon, something in the chain is misestimated. That growth budget is set by halo mass functions and baryon supply. Only a fraction of halo mass is baryons, and only a fraction of baryons become stars. The cosmic baryon fraction is measured independently, and it limits how much raw material any halo can access. To build large stellar masses early, efficiencies must rise, or the halos must be larger, or both. Even then, the gas must arrive quickly, because a baryon fraction on paper does not guarantee baryons in the central galaxy. Efficiency is a deceptively simple word, because it hides many processes. It includes how much gas reaches the central galaxy, how much forms dense molecular clouds, and how much survives feedback long enough to turn into stars. In the local universe, galaxies convert only a small fraction of available baryons into stars. Early galaxies might behave differently, but they cannot ignore gravity and energy balance. A high efficiency implies rapid cooling, high gas densities, and a feedback loop that does not immediately blow the system apart. Raising efficiency has consequences, because feedback is not a decorative detail. Massive stars flood gas with radiation, drive winds, and then explode, heating and stirring the interstellar medium. Supernova remnants can vent out of small halos, carrying metals and energy into the surrounding medium. Black hole accretion can add another energy source that regulates growth, even if the black holes are still small. The earliest black holes may grow in bursts, and their radiation can ionize and heat gas on galactic scales. If feedback is weaker early, star formation can run hotter and longer. But weaker feedback also changes later galaxy properties, including metallicities, sizes, and the faint end luminosity function. A fix for early mass can create a mismatch at later times because the universe keeps records in many observables. The same physics that builds stars early also shapes the galaxies we see billions of years later. The record is written in stellar mass functions, in metallicity distributions, and in the diffuse background light. If feedback is stronger early, galaxies self-limit and masses stay low, but then the observed brightness becomes harder to explain without invoking unusual stellar populations. The puzzle is that both directions create a new problem. The anomaly is not one knob that can be turned without moving the rest of the machine. Every adjustment changes multiple outputs, and Webb is sampling a regime where those outputs are tightly coupled. Evolved can also mean structured, and Webb images push that angle into the debate. Some candidates appear compact, and some appear to show disk-like or bulge-like light profiles. A compact core can suggest rapid central star formation, or it can suggest an early spheroid-like component. Structure implies dynamical settling, which is not expected to be fast in turbulent early environments. Settling requires time for orbits to mix, and for gas to dissipate energy, and both are challenged by frequent mergers. The visual impression is powerful because the mind reads shapes as stories. A smooth oval looks calm while clumps look chaotic, and calmness feels like age. Yet the early universe is expected to be messy, with frequent mergers and inflows along filaments. If a galaxy already looks orderly, we ask what allowed it to settle so quickly. We also ask whether we are seeing true order, or simply the brightest regions that survive the noise. Yet morphology at high redshift is a treacherous measurement. Surface brightness dimming hides low-level features and exaggerates compact cores, because faint outskirts fall below the noise. Rest frame wavelengths shift, and what looks like a disk in one band can be clumpy star formation in another. Even the same galaxy can look different depending on which filters capture which parts of its spectrum. A rest frame ultraviolet image emphasizes young star-forming knots, while rest frame optical light traces older stars more smoothly. Resolution and signal to noise also shape what we call a shape. A few bright clumps can mimic a smooth profile when blurred by the point spread function. A merger can masquerade as a single object when the separation is below the resolution limit. The early universe is full of close pairs, and close pairs are exactly what limited resolution tends to merge into one. The point spread function itself varies with wavelength, which can subtly bias size measurements across filters. So morphology hints at maturity, but it does not convict it. It adds a clue that must be cross-checked with kinematics and deeper imaging. For now, it is part of the tension, not the solution. The images are seductive, but the inference must be disciplined. In this regime, a beautiful ellipse can be a genuine disk, or a temporary alignment of star-forming clumps. Star formation rates add another axis to the definition of evolved. A galaxy can be massive because it formed stars intensely for a short time, like a brief furnace, or it can be massive because it formed stars steadily, implying an earlier start. The difference matters, because steady growth requires the galaxy to begin earlier in cosmic time. Bursty growth, by contrast, demands extreme instantaneous rates and a gas supply that can keep up. The earlier start is constrained by the cosmic timeline itself. Before recombination, baryons are coupled to radiation and cannot collapse into stars because pressure support is overwhelming. After recombination, the gas becomes neutral and can fall into dark matter potential wells, but it does not do so instantly. It must stream into halos, shock, cool and fragment, and each step consumes time. There is also the streaming velocity between baryons and dark matter, a leftover from the early universe that can suppress gas infall into the smallest halos. This is why older than expected matters more than any single age number. If the fit suggests stars already hundreds of millions of years old at Z above 10, the implied formation redshift becomes extreme. the galaxy would need to begin forming stars almost as soon as the universe became transparent. That is not impossible in principle, but it is demanding in practice. It requires early halos to assemble quickly, and it requires gas to cool efficiently despite the lack of metals. Chemical enrichment pushes in the same direction, because metals imply prior star formation. High metallicity implies repeated cycles of star birth and death, not just one brief episode. Dust implies not only metals, but also grain growth and survival in harsh radiation fields. In young galaxies, dust can be destroyed by shocks, so its presence implies both creation and persistence. The dust-to-gas ratio becomes a quiet clue because it encodes how efficiently grains form and how often they are shattered. Yet enrichment can be accelerated by top-heavy stellar populations. Massive stars live fast and die quickly, producing metals on short timescales, and they can enrich their surroundings rapidly. That can compress the enrichment clock, but it also changes the light-to-mass conversion. If the first generations are dominated by massive stars, they can make a galaxy look brighter for the same stellar mass. The same population also produces more ionizing photons, which connects directly to rionization. A top-heavy IMF makes galaxies brighter per unit mass, which can reduce inferred stellar masses. That sounds like an escape hatch, but it changes predicted supernova rates and ionizing photon output. It also changes the chemical yields, which must match observed line ratios. The solution cannot be purely photometric, it must also be chemically and energetically consistent. If the IMF is altered too much, it can overproduce metals or change abundance patterns in ways later observations would notice. The reionization era is the background pressure that every early galaxy must fit into. After the CMB, the universe becomes neutral and opaque to ultraviolet photons, creating a fog of hydrogen that absorbs short-wavelength light. The first stars and galaxies must reionize hydrogen, clearing the cosmic fog and changing how the intergalactic medium transmits light. Reionization is therefore both a milestone and a constraint. It is also a story of patchiness, because ionized bubbles grow around galaxies and then overlap. Reionization is not just a date, it is an energy accounting problem. Galaxies must produce enough ionizing photons, and enough of those photons must escape into the intergalactic medium. The timing is constrained by quasar absorption spectra, which show how much neutral hydrogen remains, and by the CMB optical depth, which records how many free electrons scattered CMB photons. Those two constraints bracket the history. They do not merely say, it happened, they limit how fast it could have happened. Early massive galaxies could help with that photon budget. Bright objects produce many photons, and their existence could ease reionization models that otherwise require numerous faint galaxies. But the same objects cannot be too rare, and they cannot violate the observed optical depth. A few bright beacons are helpful, yet they cannot rewrite the whole ionization history alone. If the bright population is real, it also raises questions about escape fraction, because dense dusty gas can trap ionizing photons. If reionization happens too early, the CMB would show a higher scattering signature. If it happens too late, quasar spectra would show more neutral hydrogen at lower redshift. The timeline is narrow, so any solution must land inside it. This is the kind of constraint that turns a speculative idea into a quantitative test. It also reminds us that early galaxies are not isolated islands, because their photons reshape the medium between them. This is the recurring pattern of the chapter. Every explanation that makes early galaxies easier to build creates a new constraint elsewhere. The universe behaves like a linked system, and Webb is pulling on one link. When one link moves, the rest of the chain tightens. The deep field is therefore not just a picture, but a stress test of a framework. So we define the anomaly precisely, because precision is the only way to test it. The claim is not that galaxies exist early because they must. The claim is that some candidates at very high redshift have inferred stellar masses, luminosities, and apparent maturity that strain typical hierarchical growth. The word typical matters because rare peaks exist, but populations require a broader shift. The anomaly is therefore statistical as well as physical, an issue of both individual properties and overall abundance. Hierarchical growth is the baseline expectation in lambda CDM. Small halos form first, then merge into larger systems over time, and the first galaxies are expected to be small and irregular. Their star formation should be bursty, because feedback can shut it off and then allow it to restart. They should also be metal poor because enrichment requires time and repeated star formation. In this baseline, the earliest luminous galaxies are expected to be scarce, and their light should be dominated by young stars. They should also be rare at the bright end, because massive halos are exponentially suppressed early. In simulations, the bright tail grows with time as halos merge and accrete, and that tail is a sensitive diagnostic of structure growth. Webb hints that the bright tail may already be populated. If that hint holds, it would mean either the halos are more abundant, or the galaxies are more efficient, or the inference is biased. The debate is about which of those possibilities can survive cross-checks. But hints are not verdicts, and the first competing interpretation is that the galaxies are not as massive or old as first thought. Photometric redshifts can be wrong, because different spectral features can mimic the same color breaks. Even correct redshifts can be paired with wrong mass-to-light ratios, because dust and emission lines can reshape broadband colors. Lensing and AGN can also inflate brightness, making an ordinary galaxy look extraordinary. In practice, several small effects can stack, producing a large apparent anomaly. This interpretation predicts that better spectroscopy and better SED modeling will move objects to lower redshift or lower mass. It also predicts that the number-density tension will soften as contamination is removed. It is the conservative path, and it has already worked for some early candidates. The history of deep surveys is full of sources that looked exotic until better data placed them in a more ordinary category. In that history, the lesson is not cynicism, but humility about inference. There is historical context here, because astronomy has seen this pattern before. In the 1990s and 2000s, early claims of very high redshift galaxies often shifted once spectroscopy improved and selection functions were understood. The Lyman break technique was powerful, but it also had interlopers, and the community learned to treat early counts cautiously. Hubble deep fields produced their own surprises, and later reanalyses often revised the extremes. Webb is more capable, yet it's still subject to the same logic of inference. The second interpretation is that galaxy evolution is faster than models assumed, without changing cosmology. Star formation efficiency could be higher in early halos, perhaps due to dense gas inflows and short dynamical times. The early universe is denser, so freefall times are shorter, and gas can collapse quickly once it cools. Feedback could be delayed, or gas could recycle rapidly, allowing repeated bursts without losing the reservoir. In this view, the timeline is tight, but the machinery runs at higher speed. This path keeps the expansion history intact, but it demands new astrophysics. It must explain how gas cools and fragments efficiently with few metals, perhaps through molecular hydrogen or through rapid enrichment in localized regions. It must explain how galaxies retain gas and metals while forming stars at extreme rates. It must also explain why the resulting galaxies do not become too compact, too metal-rich, or too luminous compared to later observations. The fix cannot be local to one epoch, because the same galaxies evolve into later populations. It must also explain why the acceleration does not overproduce stars overall. If early efficiency is high, later stellar mass functions and background light must still match observations. The extragalactic background light is a kind of fossil record of total star formation, integrated over cosmic time. A faster early start cannot become a runaway that fills the universe with too many stars. The universe allows early brilliance, but it also enforces a long-term bookkeeping. The third interpretation is that cosmology or fundamental physics differs in a way that alters the timeline. A different expansion history could give more time at a given redshift, changing the mapping from Z to age. Modified dark matter behavior could change small-scale structure growth and halo abundance, shifting when massive halos become common. These ideas are tempting because they move the clock itself, not just the hands on the galaxy formation machinery. Yet moving the clock is dangerous, because it is tied to many independent measurements, but they are constrained by the CMB, BBN, and large-scale structure. Big Bang nucleosynthesis fixes the early expansion and baryon density through light element abundances, and the CMB fixes the geometry and growth of fluctuations. Large-scale clustering and lensing map how matter assembled later. Any change must preserve the successes of the standard model while relieving the Webb tension. The challenge is to gain time or growth without losing the precise fit to the relic radiation. This is why the tone stays mysterious rather than revolutionary. The data invite bold stories, but the universe demands consistency. Each proposed fix must survive contact with multiple relics, not just with a deep field image. A single dataset can surprise us, but multiple datasets can corner us. That cornering is not a limitation, it is how cosmology earns its confidence. The chapter's core point is that evolved is a bundle of measurements and inferences. Stellar mass is inferred from light through a model, and that model includes an IMF, metallicity, dust, and star formation history. Age is inferred from SED shape and assumed star formation history, and different histories can fit the same points. The inference is not arbitrary, but it is conditional. Conditional means it can be revised when better data break degeneracies. Metallicity is inferred from spectral features and line ratios, and dust is inferred from reddening and infrared emission. Morphology is inferred from limited resolution and wavelength-dependent structure. Each inference is plausible until it collides with another inference. The anomaly is the collision, not the existence of any one measurement. The collision is where the story becomes interesting, because it forces a choice among explanations. So the anomaly is not a single number that's too big. It is a pattern that repeats across properties and across multiple objects. The pattern suggests either a systematic bias that repeats or a physical process that repeats. Repetition is what turns curiosity into a problem worth reorganizing models around. It also raises a practical question. Are we seeing the universe, or are we seeing the same modeling assumption echoed across catalogues? If it is bias, it must be a bias that survives improved reductions and independent teams. It must survive different photometric catalogues, different SED codes, and different assumptions about dust and emission lines. If it is physics, it must be physics that does not break the CMB and reionization constraints. The story is now a narrowing funnel, not a single dramatic claim. As the funnel narrows, the remaining explanations become more testable and less rhetorical. We can feel the temptation to jump to the biggest conclusion, because it would be clean. But clean conclusions are not how frontier astronomy usually resolves, because the frontier is where systematics hide. The next step is to exhaust the escape hatches inside astrophysics. We ask which assumptions are most fragile and which are anchored by independent evidence. We also ask a quieter question. What would we have believed if Webb had been just slightly less sensitive? Before rewriting cosmology, we ask how the Big Bang framework might still accommodate Webb's early universe. We test whether masses fall with better spectra, whether ages shrink with better models, and whether number counts settle with larger surveys. We also test whether lensing, AGN, or line contamination can explain the brightest cases. Only then do we decide whether the clock itself must change. The order matters, because extraordinary claims require extraordinary cross-checks. The central question stays in frame because it is the only honest organizing principle. Are these too early, too massive galaxies real evidence that the timeline needs revision? Or are they a lesson in how hard it is to translate faint infrared light into cosmic history? Webb gives us light, and we must decide how much story that light truly contains. The deep field is a mirror held up to our models, and the reflection is slightly distorted. The next chapter follows the escape hatches one by one, and it treats each as a serious suspect. Some will fail quickly, and some will fail only after they seem to work. The mystery is not whether we can explain one galaxy, but whether we can explain the whole population without breaking the rest of the universe. That is the standard of proof, and it is why the anomaly remains so compelling. The crisis is not a single impossible galaxy, glowing alone like a mistake in the dark. The crisis is a population that looks too bright, too heavy, and too mature for its assigned time. On a timeline measured in hundreds of millions of years, these objects seem to arrive already grown, already settled into the kind of mass we associate with later cosmic chapters. In the standard timeline, the clock is tight but not arbitrary, because it is set by expansion, cooling, and collapse. The age of the universe at a given redshift is not a guess. It is a consequence of the measured expansion history. That history is encoded in the scale factor, and it is cross-checked by supernovae, the CMB, and baryon acoustic oscillations. If the clock is right, then the light must be misread, boosted, or produced differently. That is the premise of this chapter. Before we accuse the universe of running fast, we audit every ordinary way a galaxy can look older than it is, so we treat the most grounded fixes like suspects. Each one can explain part of the evidence, and each one leaves a trace elsewhere. The art is not picking a favourite explanation, but checking whether a fix creates contradictions in other data, spectra, number counts, chemical yields, or the physics of gas and dust. In practice, the audit feels like forensics, because every assumption leaves residue in a fit. First suspect is dust, because dust can turn youth into apparent age. Dust absorbs and scatters blue light, then reshapes the spectrum into redder colours. Visually, it is the difference between crisp, bluish starlight and a dimmer glow that looks warmer, as if the galaxy has already cooled into maturity. On screen, dust is not a cartoon smudge. It is a complex, mottled veil threaded through star-forming regions. Dust matters because our first measurements are often just colours in a handful of filters, not a full spectrum. The early JWST images arrive as points on a graph, fluxes in NIRCam bands. Then we infer a story. If dust is present, the story can flip, because dust does not merely dim light uniformly. It dims short wavelengths more than long wavelengths, and that wavelength dependence is exactly what we use to estimate age. In said fitting, red can mean old stars, or it can mean obscured young stars. The degeneracy is strongest when photometry is sparse and uncertainties are large, which is often true for the faintest and most distant candidates. A galaxy can be fit as a relatively old population, with a high mass-to-light ratio, or as a younger population hidden behind dust, with a much lower mass. Both solutions can match the same data points, and the difference can be a factor of several in the inferred stellar mass. Dust attenuation curves encode how extinction changes with wavelength. A steeper curve suppresses UV strongly, while a greyer curve reddens more gently. In plain terms, the curve tells us whether dust acts like a sharp blue filter or a softer veil. That choice changes how much intrinsic UV light we must assume, and therefore how many young stars we infer. It also changes the inferred star formation rate, because UV is our most direct tracer of massive, short-lived stars. The curve is not universal, and early galaxies may not follow Milky Way rules. Grain size distributions, compositions, and geometry can shift the effective reddening. Small grains tend to produce stronger wavelength dependence, while larger grains can make attenuation greyer. Even the spatial arrangement matters. Dust mixed with stars does not behave like dust in a simple foreground screen. Clumpiness matters too, because porous dust can let blue light leak through while still reddening the average colour. Historically, this has been a recurring lesson in extragalactic astronomy. The Calzetti attenuation law, derived from local starbursts, became a workhorse because it worked often enough. Yet it was never guaranteed to apply at redshifts where metallicities are low and interstellar media are turbulent. When we push to the first billion years, we are implicitly betting that a local empirical rule still holds. That bet is not reckless, but it is a reminder that our priors were trained in a calmer neighbourhood. Dust also interacts with star formation history in the fit. A dusty burst can mimic an older, smoother population with a higher mass-to-light ratio. The model sees red colours and tries to explain them, and if dust is constrained too tightly, age becomes the easiest knob to turn. That is why dust is not a cosmetic correction, but a structural uncertainty in the inference. In the language of statistics, dust and age are covariant, and the covariance can dominate the error budget. Infrared data helps because it samples rest frame optical light at high redshift. It can reduce reliance on UV colours, but it cannot fully break the trade. At redshift 10, what we call infrared is often just the galaxy's visible light stretched by expansion. Those longer wavelengths carry information about older stars, but they also carry the imprint of dust geometry and emission lines. Even the Balmer break, which we use as an age indicator, can be mimicked by line-boosted photometry. Even with infrared coverage, dust and age can still trade places. A small change in assumed attenuation can move inferred stellar mass by large factors. The effect is amplified by the fact that stellar population models have steep mass-to-light evolution at young ages. When a population is only tens of millions of years old, a modest shift in age can change luminosity per unit mass dramatically. That steep slope is why early-time errors feel so unforgiving. Dust is also evidence, not just a nuisance parameter. If significant dust exists early, it implies rapid metal production and grain formation. Dust grains are built from heavy elements, carbon, silicon, oxygen, iron. So dust is a fossil of prior generations of stars. In that sense, dust does not simply hide star formation. It testifies that star formation has already been intense. The very act of reddening becomes a clue about how quickly the first enrichment happened. That implication creates a second constraint on the dust suspect. Dust that fixes colours must also be physically plausible given enrichment timescales and feedback. Grain formation can occur in supernova ejecta, and later grain growth can proceed in dense molecular clouds, but both routes require conditions that are not guaranteed in tiny early galaxies. If we invoke heavy dust to explain redness, we must also explain how metals formed quickly and how grains survived shocks that tend to destroy them. Survival is not automatic, because reverse shocks can shred grains before they ever mix into the interstellar medium. There is also a subtle observational consequence. Dust that absorbs UV should re-radiate energy in the infrared, shifting it into far infrared and sub-millimeter wavelengths. For the earliest galaxies, those wavelengths are difficult to detect, and non-detections can be ambiguous. Still, the energy budget is a check. If we hide too much UV behind dust, we should eventually see the heat somewhere. In visual terms, the missing blue light should reappear as a faint cold glow in longer wave maps. Second suspect is nebular emission line contamination. Ionized gas around young stars emits strong lines that can flood broadband filters. The visual here is deceptively simple. A filter measures total photons, and a narrow spike in wavelength can masquerade as a broad rise in the continuum. It is the difference between a smooth hillside and a needle peak, blurred by the instrument into a false plateau. At the relevant redshifts, O3 and H-beta can land inside key NIRCam bands. A single boosted band can mimic a continuum rise. When the photometry shows one point sitting high above its neighbours, the FIT may interpret it as a spectral break, or as the red side of an older stellar population. Yet the true cause might be a few bright lines from gas, not a mountain of stars. The danger is greatest when the boosted band anchors the mass estimate, because rest frame optical light is where we usually trust mass-to-light ratios. Broadband photometry counts photons, not their origin. If line photons are treated as starlight, the inferred continuum level becomes too high. That pushes SED fits toward older ages or higher masses, because the model tries to explain extra flux with more stars. The mass inflation can be dramatic, especially when the boosted band anchors the rest frame optical where mass-to-light ratios are usually inferred. In extreme cases, a line can contribute a large fraction of the bandpass flux, and the FIT barely notices. This is not a new problem, but JWST makes it urgent. In earlier eras, broadband surveys at high redshift already struggled with line contamination, particularly in Spitzer, Iraq bands. The community learned to treat extreme emission line galaxies as a special class, and to use color diagnostics to flag them. JWST pushes the same issue into a regime where the lines can be even stronger and the galaxies even younger. The old lesson returns, but the stakes climb because the timeline is shorter. Extreme equivalent width galaxies are expected in the early universe. Low metallicity and high ionization can make lines unusually strong. In physical terms, hot, massive stars produce hard ultraviolet photons that strip electrons from oxygen and hydrogen. When electrons recombine and cascade down energy levels, they emit light at specific wavelengths, and those lines can dominate the observed flux. The gas becomes a neon sign wrapped around the stars, and the sign can outshine the building. So line contamination is not an exotic loophole. It is a common early universe condition that becomes dangerous when filters are broad. A broad filter is like a wide bucket, and a narrow line is like a sudden downpour. The bucket fills, and the measurement looks like a steady rain. The more distant the galaxy, the more likely those key lines slide into exactly the bands we rely on. Spectroscopy is the corrective tool because it separates spikes from continuum. When lines are measured directly, broadband masses can be revised downward. A spectrum turns a suspicious photometric bump into a set of identifiable features, each with a wavelength that also confirms redshift. In a single observation, spectroscopy can test both the distance and the mass estimate. Visually, the plot changes from a few dots to a jagged skyline, where the culprit peaks stand out. Yet spectroscopy introduces its own tension. If lines are extreme, they imply intense recent star formation and high ionizing photon production. That implication must match reionization constraints and the observed line ratios. A line-based fix can solve mass while raising questions about physical conditions, because the same photons that power lines also leak into the intergalactic medium. The galaxy becomes lighter on paper, but more intense in its radiation output. Line ratios are not just decorative. They encode electron temperature, density, metallicity, and ionization parameter, which is a measure of how intense the radiation field is relative to gas density. If early galaxies show unusually high O3 H-beta ratios, we infer hard radiation fields and low metallicities. Those inferences then feed back into models of stellar populations, because metal-poor stars are hotter and produce more ionizing photons. The spectrum becomes a diagnostic panel, and every ratio is a gauge. Third suspect is bursty star formation, which changes how we interpret brightness. A short, intense burst can dominate light without requiring huge stellar mass. In a burst, a small fraction of young, massive stars can outshine the older population. The galaxy looks heavy if we assume the light is long-lived. The visual is a city at night during a festival, brilliant for a moment, then suddenly ordinary. This is a basic trap in stellar population inference. Massive stars live fast and die young, shining intensely for only a few million years. If we catch a galaxy during that brief window, its luminosity can spike. The mass, however, does not spike in the same way, because most of the mass is in longer-lived, lower-mass stars that contribute less light. That mismatch is why a burst can counterfeit maturity. Bursts also produce strong nebular lines and blue continua. That links this suspect to the line suspect, and it suggests a combined explanation. A burst can both brighten the continuum and flood filters with emission lines, creating a double-counting risk. The photometry then looks like a mature stellar population, when it may be a temporary flare. In the worst case, the FIT interprets the flare as an accumulated history. Bursty histories are expected in shallow early halos. Feedback can shut off star formation, then gas can cool and restart, producing episodic growth. In small halos, a few supernovae can heat or expel gas, and the recovery time can be comparable to the age of the system. The result is not a smooth, steady build, but a rhythm, light, then quiet, then light again. That rhythm is written into the gas dynamics, not into our desire for simple models. This matters for inferred ages. A recent burst can hide an older, smaller underlying population, or it can mimic an older population if dust is heavy. The underlying population might be modest, but the burst makes the galaxy appear as if it has been forming stars for a long time. Alternatively, dust can suppress the burst's blue light, and the combination can masquerade as an older, redder system. The same galaxy can wear multiple disguises depending on which photons escape. Bursts also matter for number counts. If many galaxies are caught during brief luminous phases, surveys can overestimate typical masses and luminosities. A snapshot of the universe is not the same as an average over time. If duty cycles are short, the bright fraction can be misleading, and the inferred typical growth rate can be biased upward. The question becomes statistical. How often are we catching galaxies at their brightest moment? But burstiness leaves fingerprints in variability, line strengths, and inferred duty cycles. Models must reproduce the observed fraction of bright objects without overproducing stars overall. If bursts are too frequent or too intense, the integrated stellar mass density becomes too high by later epochs. That is a hard constraint, because later surveys measure how much stellar mass actually exists. The universe cannot keep forming stars at a frantic pace without showing the cumulative result. There is also a dynamical angle to burstiness. Gas inflows at high redshift can be cold and dense, funneled along filaments into the centers of halos. The inflow can trigger rapid star formation, and then feedback can disrupt it. The cycle is not arbitrary. It is tied to the gravitational potential, the cooling time, and the ability of radiation and supernovae to couple to gas. In visuals, those filaments look like faint rivers feeding a bright knot, then dispersing under the blast of newborn stars. Fourth suspect is gravitational lensing, because gravity can counterfeit luminosity. Foreground mass bends light and magnifies background galaxies. The visual is cinematic. A distant galaxy's light is stretched and brightened as it passes a foreground halo, like an image seen through a warped glass. Even when the distortion is subtle, the brightness boost can be decisive for detection. Strong lensing is obvious when arcs appear, but modest magnification can be subtle. Even factors of 2 matter when the luminosity function is steep. A magnification of 2 does not sound dramatic, yet on the exponential tail of a distribution, it can move a source from rare to common, or from undetectable to headline making. In practice, it can turn a marginal candidate into a too early galaxy. Selection effects amplify the lensing suspect. Flux-limited surveys preferentially include magnified sources, because magnification lifts them above detection thresholds. This is magnification bias, and it can inflate the apparent abundance of bright high-redshift galaxies. The bias grows when the intrinsic counts fall rapidly with brightness, which is exactly what we expect at the bright end. The survey does not lie, but it does listen more carefully to the loudest voices. Deep fields are small, and small fields are vulnerable to chance alignments. A single foreground group can raise magnification across a region without dramatic arcs. The magnification field can be smooth enough that no one object looks obviously lensed, yet the entire sample is nudged brighter. That is the dangerous regime because it hides in plain sight. The image looks clean while the statistics quietly drift. Lensing can be modelled using foreground galaxy catalogues and mass reconstructions. It can also be tested statistically by looking for correlations with foreground structure. If bright high redshift candidates cluster behind foreground overdensities, that is a clue. Conversely, if they appear uniformly across regions with little foreground mass, lensing loses explanatory power. The suspect can be interrogated, but only if we map the foreground with equal seriousness. Yet lensing cannot explain everything. If many bright candidates sit in regions with little foreground mass, lensing becomes an incomplete suspect. The lensing optical depth is limited, and the probability of significant magnification is not high across random lines of sight. Lensing can rescue some objects, and it can bias some counts, but it cannot simply rewrite the whole early universe. It is a scalpel, not a bulldozer. There is also a conceptual check that lensing forces on us. Lensing conserves surface brightness, so it stretches area while boosting total flux. High-resolution images can sometimes reveal this, because a lensed source may look larger or more distorted than expected for its redshift. When the morphology is compact and symmetric, lensing becomes harder to argue, though it is never fully ruled out. The absence of arcs is not innocence, but it is a missing fingerprint. Fifth suspect is the initial mass function, because the IMF sets the light-to-mass conversion. If early stars were more massive on average, galaxies would look brighter per unit mass. The IMF is a statistical rule, not a law of nature, and it is inferred indirectly even in the local universe. Historically, Salpeter's early work and later refinements like Krupa and Chabrier became defaults because they matched nearby stellar populations well. A top-heavy IMF would reduce inferred stellar masses for the same observed luminosity. It would also increase ionizing photon output and supernova rates. In plain language, if a galaxy forms more massive stars than we expect, it becomes a brighter beacon with less long-lived mass. That sounds like an elegant fix, but it comes with a cascade of consequences. The fix changes not just the brightness, but the entire life cycle of the galaxy's baryons. That change has consequences that cannot be hidden in photometry. More massive stars mean faster chemical enrichment and different abundance patterns. They also imply more core collapse supernova per unit stellar mass, which injects energy and metals into the interstellar medium. If we invoke a top-heavy IMF, we must accept a universe that enriches and stirs itself more aggressively. The early intergalactic medium would be seeded more quickly, and later galaxies would inherit that history. It also means stronger feedback from winds and explosions. A top-heavy IMF can help build brightness early, while also making it harder to retain gas. Small halos might be blown out more easily, suppressing later star formation. The IMF suspect therefore interacts with the burst suspect and the feedback recipes in simulations. A galaxy that shines easily may also self-sabotage its future growth. So the IMF suspect is powerful but risky. It must fit metal yields, rionization, and later stellar populations, not just early SED fits. If the IMF were dramatically different at high redshift, we might expect signatures in the chemical composition of later galaxies and in the integrated background light. The fix cannot be local. It echoes forward in time. The universe would remember, even if our early photometry is ambiguous. Sixth suspect is rapid assembly in rare peaks, the densest early regions. In lambda CDM, the earliest halos form where initial fluctuations were highest. The early universe is not perfectly smooth. It is seeded with tiny density variations that grow under gravity. Rare peaks are the high points in that initial landscape. In visualizations of the primordial density field, they are the bright knots that collapse first. Rare peaks collapse first and accrete quickly. They can host surprisingly massive galaxies early, without changing the overall cosmological model. In those regions, gas supply can be abundant, merger rates can be high, and dynamical times can be short. The galaxy's growth is not typical, but the model allows extremes. The question is whether JWST is seeing the extremes, or something closer to the rule. This suspect connects directly to survey geometry. JWST's first deep fields cover tiny areas, and tiny areas can oversample extremes. If you throw a small net into a turbulent sea, you might catch a strange fish and think the ocean is full of them. Cosmic surveys have the same risk when the field of view is narrow. The first fields are precious, but they are not automatically representative. Cosmic variance is not a footnote here. If early surveys landed on overdense lines of sight, the inferred number densities can be biased high. The variance is not just statistical noise, it is the universe's real structure imprinting itself on a small sample. Two fields of the same depth can yield different stories simply because they look through different cosmic neighborhoods. The mystery can be amplified by geography. The fix is more sky, not just deeper sky. Wider surveys reduce variance and reveal whether the early bright population is typical or exceptional. Depth tells us how faint we can see, while area tells us how representative our view is. For population claims, area is often the more decisive currency. The narrative shifts from "we found them" to "how often do they appear." Yet rare peaks have limits. Even the highest peaks must follow the halo mass function, and the predicted abundance drops sharply at early times. If confirmed counts remain high across many independent fields, rarity alone cannot carry the timeline. The suspect then becomes an accomplice, not the culprit. At that point, the pressure returns to star formation efficiency and to the astrophysics inside halos. There is a deeper implication here. If early bright galaxies are common, then the average efficiency of turning baryons into stars must be high. That pushes against feedback expectations, because feedback is supposed to be especially effective in small halos. Rare peaks can hide high efficiency in a few places, but they cannot make it universal. The universe would need to be unusually good at building stars early, and unusually consistent about it. Seventh suspect is black holes and AGN, because accretion can add light that looks like stars. A growing black hole can produce a compact, bright continuum. In images, an AGN can sit like a point of white-hot light at the centre, and in low-resolution photometry, it can blend into the galaxy's starlight. The visual is a tiny furnace embedded in a faint extended host. If AGN light is fit as stellar light, inferred masses and ages rise. The galaxy seems mature when part of the luminosity is non-stellar. The effect can be especially misleading if the AGN continuum is relatively featureless across the observed bands. The fit then assigns that smooth brightness to an older stellar population, because that is a familiar way to make red light. A point source can quietly distort an entire population inference. AGN can also heat dust, altering infrared colours. That can confuse attenuation estimates and push fits toward older solutions. A dusty torus around an AGN emits strongly in the infrared, and if we interpret that emission as starlight reddened by dust, we may overestimate stellar mass. The same photons can be counted twice, once as evidence of stars and again as evidence of dust. The bookkeeping becomes treacherous when the source is unresolved. Rapid black hole growth is already hinted by early quasars. If billion solar mass black holes exist by redshift 7, accretion can be efficient early. Those quasars were discovered before JWST, and they already forced theorists to consider massive seeds, rapid growth, or both. The question is whether less extreme, more common AGN are also present in the galaxies JWST is now finding. If they are, then galaxy light is partly accretion light, and the timeline debate shifts. But AGN leaves signatures. Broad lines, high ionization features, X-ray emission, and mid-infrared excess can reveal accretion. Even narrow emission lines can carry AGN fingerprints, because the ionizing spectrum is harder than that of normal stars. In principle, the suspect is detectable. In practice, the evidence can be faint. The early universe does not make diagnostics easy, because distances dilute everything. The problem is sensitivity and contamination. Many early candidates are too faint for clean AGN diagnostics, so the suspect can hide behind noise. X-ray observations may not reach the needed depth, and mid-infrared coverage can be limited. Spectra can be noisy, and line identifications can be ambiguous at the edge of detectability. We're often trying to separate a whisper from the hiss of the detector. AGN also complicate feedback. If black holes grow early, their energy can regulate star formation, which changes the galaxy's later evolution. Accretion-driven winds can heat gas, expel it, or prevent it from cooling, and that can suppress star formation even as the galaxy appears bright. The timeline can be saved on paper, while the physics becomes more intricate. The galaxy may look mature, while its future is being throttled. So AGN can reduce inferred stellar mass while raising a new question. How did the black hole seed form and grow so quickly without violating other constraints? If black holes are common contributors to early luminosity, then early galaxies are not just stellar factories, they are also accretion engines, and that changes how we interpret their role in ionization and chemical enrichment. It also changes what typical means, because typical would include hidden engines. Now the suspects begin to overlap, and the plot thickens. Dust can redden a burst, lines can boost a band, and lensing can magnify the whole package. A compact galaxy behind a modest lens caught during a burst, with extreme O3 lines and a slightly greyer dust law, can look like a massive old system. None of those ingredients is impossible, but the combination can be hard to diagnose with limited data. The unsettling part is how naturally the ingredients align in the same direction. A single correction can lower a mass estimate by a factor of 2. Several corrections together can lower it by an order of magnitude. That is why the debate is not resolved by one clever reanalysis. The inference chain has multiple weak links, and they can fail in the same direction. When the errors correlate, confidence can be an illusion. There is also a psychological dimension to the problem. Our models are trained on the nearby universe, where star formation histories are often smoother and dust laws are better calibrated. When we see a red, bright object, our instincts lean toward age and mass. JWST forces us to ask whether those instincts are reliable in a universe that is still assembling its first stable structures. What looks like an old city may be a young city under smoke. The grounded strategy is to model all effects together. That means joint fits with flexible star formation histories, nebular emission, dust laws, and AGN components. It also means admitting that the parameter space is wide. When we allow more freedom, uncertainties grow, and the most confident-looking early mass estimates can soften into ranges. The mystery does not vanish, but it becomes more honestly quantified. It also means using spectroscopy to anchor redshifts and line strengths. Without spectra, broadband fits can drift into plausible but wrong corners of parameter space. A photometric redshift can be pulled by a single band, especially when emission lines are present. A spectroscopic redshift pins the distance, and distance is the lever that turns flux into luminosity. Once distance is fixed, the remaining debate becomes about physics, not geometry. Simulations are being updated in parallel because the data are now a target. Groups adjust star formation efficiency, feedback recipes, and dust production models. The process is iterative. Observations reveal a discrepancy. Theorists test which physical knobs can move, and then new predictions are compared to the next wave of data. In a sense, JWST has turned early galaxy modeling into an active engineering problem. Some updates increase early star formation by exploiting short dynamical times and dense inflows. Others change how feedback couples to gas in small halos. In high redshift environments, gas densities can be high, and cooling can be efficient, which can make star formation more rapid. Yet feedback may also be more violent, and the balance between these effects is not settled. The same density that fuels star formation also makes radiation pressure and supernova shocks harder to ignore. Dust treatments are also being revised. Early dust may form rapidly in supernova ejecta, then grow in dense clouds, changing attenuation and infrared emission. The survival of dust in supernova shocks is debated, and the efficiency of grain growth depends on density and metallicity. These details matter because dust is both a reddening agent and a record of past star formation. When we change dust physics in a simulation, we change both the colours and the implied history. Nebular emission is being treated more carefully in forward models. Simulations now predict line-equivalent widths and broadband colours, not just stellar masses. That is a shift in philosophy. Instead of fitting masses first and adding lines later, models try to generate the observables directly. When a simulation produces a galaxy, it also produces the spectrum that JWST would see. The comparison becomes more direct, and the excuses become fewer. These updates can bring models closer to JWST observations without altering Big Bang cosmology. They show that astrophysics still has room to maneuver. The early universe is a laboratory where small-scale physics, feedback, dust, radiative transfer, can dominate what we infer from light. The caution is that the room to maneuver is not infinite, because other epochs constrain the same parameters, but the maneuvering is constrained by other epochs. A model that makes early galaxies bright must still match later mass functions and the extragalactic background light. It must also respect Ryanization constraints from the CMB optical depth and quasar absorption. More early light changes the ionization history, and the universe keeps receipts. The receipts are written in the transparency of intergalactic hydrogen and in the faint glow of accumulated starlight. Ryanization is a particularly strict accountant. If early galaxies are producing many ionizing photons, those photons must either escape into the intergalactic medium or be absorbed locally. Escape fractions, dust absorption, and gas geometry become critical. A model that solves brightness by invoking intense star formation must still explain how the ionizing budget fits the observed timing of ryanization. If too many photons are trapped, the galaxies can be bright yet ineffective at ryanizing, and that mismatch becomes its own tension, and it must respect chemical evolution. If early stars are too efficient, metals and dust may be overproduced relative to what later galaxies display. Metallicity measurements at later times, and the distribution of metals in the intergalactic medium set limits. The early universe can be productive, but it cannot be recklessly productive without leaving traces. Those traces appear in absorption lines, in stellar abundances, and in the cooling properties of later gas. So each fix is a trade. Lowering inferred masses can require more extreme bursts, or more extreme lines, or more extreme dust, each with consequences. The suspects are not independent, and the constraints are not isolated. The story is a web, and pulling one thread tightens another. The more we save the timeline in one place, the more we must justify the cost elsewhere. The remaining friction is the point of this chapter. Even after conservative corrections, some objects still look uncomfortably luminous for their time. Their inferred masses may shrink, yet their abundance can remain high. The tension shifts from individual galaxies to population statistics, and that shift changes the weight of the evidence. A single object can be a trick of light, but a persistent pattern demands a deeper explanation. In some analyses, number densities remain high enough to strain typical halo growth rates. The tension shifts from how can this one galaxy exist to how can so many exist at once. That distinction is crucial, because populations are harder to dismiss. A single outlier can be lensing, but a persistent excess suggests a systematic or new physics. It also forces a more careful look at how we translate counts into cosmic history. Population statistics also force a different kind of rigor. They depend on selection functions, completeness corrections, and the shape of the luminosity function. Small changes in assumed completeness at the faint end can ripple into the bright end when we fit models. The early JWST era is therefore not just about finding galaxies, it is about quantifying what we might have missed. The invisible part of the sample can steer the visible conclusions. We are left with a layered explanation that feels unsatisfying but realistic. The timeline may be saved, yet only by stacking several subtle effects. That stacking is not a failure of cosmology, it is a reminder of how inference works at the frontier. The earliest universe is where small assumptions become large conclusions. It is also where the difference between plausible and proven becomes painfully important. There is also a philosophical question hiding beneath the technical debate. When we look back to the first few 100 million years, we are not observing a calm, mature cosmos. We are observing a system in rapid transition, where definitions like typical galaxy may not even apply. Should we expect smooth histories and familiar dust laws, or should we expect extremes as the default? If the first galaxies are chaotic by nature, then our neat categories may be the real anachronism. Still, the audit has a limit. If the best astrophysical corrections cannot fully relieve the pressure, then the clock itself returns to the suspect list. That is the transition to the next chapter's stakes. If astrophysics cannot close the gap, we confront cracks already present in cosmology. At that point, the debate stops being about galaxies alone and becomes about the scaffolding behind them. The Hubble tension becomes part of the same story, because it questions the expansion rate that sets the timeline. Other expansion puzzles join it, demanding new tests. When the expansion history is uncertain, the inferred ages at high redshift shift as well. The question becomes uncomfortably direct. Are we misreading galaxies or miscalibrating the universe? If the calibration is off, then every derived age inherits the error. And the central question stays sharp. Are Webb's too early galaxies an inference mirage, an astrophysical sprint, or a sign the universe's schedule is wrong? Each option carries a different kind of discomfort. A mirage implies our methods are fragile, a sprint implies early physics is more extreme than we thought, and a wrong schedule implies cosmology itself needs revision. The mystery is not which answer we prefer, but which answer survives the full set of constraints. We end here with a controlled uncertainty. The Big Bang framework is not dismissed, but it is under audit, and the audit is becoming more expensive. Every new spectrum, every wider field, and every improved simulation adds a line item to the balance sheet. The mystery is not fading, but sharpening. With each correction we apply, we learn whether the tension was a trick of light or a deeper message. Next, we step beyond galaxy physics and into cosmology's own balance sheet. We ask what happens if the timeline cannot be saved by dust and lenses alone. Still, the audit has a limit. If dust, lines, lensing, bursts, and AGN cannot close the gap, the pressure shifts from galaxies to cosmology itself. The camera pulls back from individual smudges of light, and the frame fills with grids, axes, and residuals, numbers that refuse to settle. Cosmology has its own anomaly, older than Webb's deep fields and harder to ignore. It is the Hubble tension, a disagreement about how fast the universe expands today. It sounds like a technical quarrel, yet it touches the conversion table we use to turn redshift into time. The name carries history. Edwin Hubble's original 1920s measurement was crude by modern standards, but it established the idea of expansion as an observable fact. Over the next century, the value of H0 swung wildly as methods improved, then slowly converged, until it split again with better data. One method builds H0 locally, rung by rung, using geometric distances and calibrated standard candles. Another infers H0 from the cosmic microwave background by fitting a full early universe model. The two approaches do not merely disagree, they disagree in a way that has survived years of scrutiny. The local distance ladder begins with geometry. Parallax measures tiny shifts in a star's apparent position as Earth orbits the Sun, turning angles into distances. Those distances calibrate Cepheid variables, whose pulsation periods correlate with intrinsic luminosity, and that correlation becomes a ruler we can carry outward. From Cepheids, the ladder climbs to Type Ia supernovae. These explosions are not perfectly identical, yet their light curves can be standardized with empirical corrections. Once calibrated, they extend the distance scale far beyond the local group, into the smooth Hubble flow where peculiar velocities matter less. The other method looks backward, not outward. The CMB is a photograph of the universe when it was about 380,000 years old, when electrons and protons combined and photons finally streamed freely. Those photons have been stretched into microwaves by expansion, and their temperature fluctuations encode early physics. The local distance ladder, anchored by parallax and Cepheids, tends to prefer a higher H0. The CMB, interpreted through LCDM, tends to prefer a lower H0. On screen, the two probability curves overlap only slightly, like two stories that share a few words but diverge in meaning. This is not a small bookkeeping dispute. The difference is several kilometers per second per megaparsec, large compared with quoted uncertainties and persistent across teams. It is large enough that, if it is real, it implies a shift in the cosmic budget or the cosmic rules. If the local value is right, the universe expands faster now than LCDM predicts. If the CMB value is right, local measurements contain hidden systematics or unmodeled astrophysics. Either way, the tension forces a question that cosmology would rather postpone. What exactly is being assumed when we translate data into parameters? Why does this matter for Webb's early galaxies? Because H0 is not just a number for today. It is a boundary condition that shapes the entire expansion history. When you change the boundary, you shift the curve, and the curve is what turns redshift into a timeline. In LCDM, the age of the universe is tied to the integral of expansion over time. A higher H0 generally implies a younger universe, if other parameters remain similar. That relationship is not a slogan. It is built into the Friedmann equations that connect energy density to the scale factor's evolution. A younger universe tightens the early timeline. It leaves even less time to assemble massive galaxies by redshift 10 or 15. The visual becomes a shrinking ruler laid across the first billion years, with the tick marks crowding together as the expansion rate rises. So the tension cuts both ways. A higher H0 can signal missing physics, yet it can also worsen the too early problem if the early clock runs faster. The same adjustment that eases one discomfort can intensify another, and that is why the debate feels so stubborn. The deeper point is that redshift is not a direct timestamp. Redshift becomes time only after choosing a model for how the scale factor evolves. What Webb measures is wavelength stretching, plus flux and morphology, and then we compute the rest. We often speak as if z equals age, as if the universe carries a built-in calendar. In reality, the calendar is computed, and the computation depends on assumptions. Even the phrase "look back time" hides a model choice, because it is a derived quantity, not a raw datum. Change the expansion rate at early times and the mapping from redshift to cosmic time shifts. The same photons can correspond to a different age, without changing their wavelength. The narration lingers on a graph where multiple curves pass through the same redshift, yet land on different times. That is the opening for new physics. Not a new beginning before the Big Bang, but a modified early chapter that changes how we translate light into history. The stakes are subtle. It is not about rewriting the existence of the hot early universe, but about revising the details that connect epochs. So we widen the lens, from galaxy formation details to the scaffolding that sets the cosmic clock. The question becomes whether LCDM is complete enough for Webb. The shot widens again, from galaxies to the CMB sky, from star formation to the shape of the power spectrum. The standard model is not a single equation. It is a linked fit to many datasets, where parameters are constrained together and trade off against each other. When one parameter moves, others often shift to preserve the same observable features, and that is both a strength and a trap. The CMB is central because it is precise. Its acoustic peaks encode the baryon density, dark matter density, curvature, and the sound horizon scale. Those peaks arise from pressure waves in the early plasma, frozen into a pattern when photons decoupled from matter. The sound horizon is crucial. It is the distance sound waves travelled in the early plasma before recombination froze the pattern in place. In plain terms, it is the size of the early universe's ringing imprint, a standard ruler projected across the sky. CMB inferred H0 is not measured directly. It is derived by combining the observed angular scale of the sound horizon with a model for early universe physics. The CMB tells us how big the ruler looks, and the model tells us how big the ruler actually was. If we alter early physics, we can change the sound horizon. That can shift the inferred H0 while leaving the CMB sky looking almost the same. The peaks can remain in familiar positions, even as the underlying conversion from angles to distances quietly changes. That is why the Hubble tension is a portal to new physics. It suggests the early universe might contain an ingredient that LCDM leaves out. The portal is narrow though, because the CMB is not a single number. It is a spectrum with thousands of correlated measurements, but every new ingredient solves one puzzle while risking another. Cosmology is a web, and the web is tight. Pull one strand to relieve the Hubble tension, and you may tug on rionization, lensing, or the abundance of clusters. The first major candidate is early dark energy. It is a brief additional energy component that becomes important before recombination, then fades away. The key word is brief, an episode rather than a permanent new substance dominating the cosmos. Early dark energy increases the expansion rate at early times. Faster early expansion shrinks the sound horizon, changing how the CMB translates into H0. The animation shows the early universe expanding a little more quickly, leaving less time for sound waves to travel before decoupling. With a smaller sound horizon, the CMB can accommodate a higher H0 today. The model can move the CMB inferred value toward the local ladder. It is a clever move. Change the ruler, and you change the inferred distance scale without changing the observed angles. This sounds like a clean fix, but it has costs. Changing early expansion also changes how matter perturbations grow, and growth is measured later. Density fluctuations do not merely sit there. They evolve under gravity, and that evolution is sensitive to the expansion rate. Early dark energy can suppress or enhance structure formation depending on its timing and coupling. That affects the abundance of halos that host early galaxies. Even a few % change in the energy budget at the wrong time can shift when the first rare peaks collapse. For Webb's problem, the direction matters. If early dark energy speeds early expansion, it can reduce the time available at fixed redshift. Yet it can also change the growth rate of perturbations, potentially altering when massive halos become common. The same change can help one tension and hurt another. The model must thread a needle. It must raise H0 without spoiling the CMB peak structure and without breaking baryon acoustic oscillation distances. It must also respect Big Bang nucleosynthesis. BBN depends on the expansion rate during the first minutes, and light element abundances are unforgiving. Deuterium and helium are not just relics. They are accounting records of the early expansion rate. So early dark energy is not a free dial. It is a constrained episode squeezed between the CMB, BBN, and the later universe's clustering. The visuals become a narrow corridor of allowed parameter space, with red regions marking exclusions. The second family of ideas changes dark matter itself. Dark matter is the gravitational scaffolding for halos, and halo timing is the bottleneck for early galaxies. If the scaffolding forms differently, the first luminous structures may arrive earlier or later. In LCDM, dark matter is cold and collisionless. Cold means it has negligible thermal motion, so it can clump on very small scales. Collisionless means it mostly interacts through gravity, allowing structures to form hierarchically from tiny seeds. If dark matter is not perfectly cold, small-scale power is reduced. That changes the first halos, the merger tree, and the early supply of dense potential wells. The cosmic web becomes smoother at the smallest scales, and the first steps of assembly shift. Warm dark matter is one variant. Its particles have enough early motion to erase small-scale fluctuations, delaying the formation of small halos. In simulations, the smallest clumps simply never appear, and the early universe looks less grainy. Warm dark matter can ease some small-scale problems in the local universe, but for Webb, it often makes early massive galaxies harder, not easier. If the building blocks arrive late, the larger structures struggle to assemble in time. If small halos form later, the whole hierarchy shifts later. The earlier star formation is delayed, and the timeline becomes even tighter. The narrator's tone turns cautious, because a fix for one scale can become a complication at another. Another variant is self-interacting dark matter. Here, dark matter particles scatter off each other, reshaping halo cores and changing internal densities. Instead of sharp cusps, halos can develop softer cores, altering how gas behaves in the same potential. Self-interactions can lower central densities and alter how baryons cool and settle. That can change star formation efficiency and feedback coupling. If gas is less tightly bound, stellar winds and supernovae may expel it more easily, or, in some regimes, allow it to settle more gently. For early galaxies, the effect is ambiguous. Lower central density can slow early star formation, yet altered baryonic response can also reduce disruptive feedback. The ambiguity matters, because Webb's galaxies are inferred from light, and light depends on how efficiently gas turns into stars. A third variant involves ultralight axion-like fields. These behave like waves on kiloparsec scales, creating a quantum pressure that smooths structure. The imagery shifts to rippling interference patterns, as if gravity itself were working through a soft, wave-like medium. Wave-like dark matter suppresses small halos and creates soliton-like cores. It can change early halo assembly and the distribution of dense regions. In some parameter ranges, it produces distinctive core sizes that could be tested with lensing and dwarf galaxy dynamics. Again, the danger is delay. If structure is smoothed too much, the first luminous objects appear later, and Webb's early light becomes harder to explain. A universe that is too smooth at small scales struggles to produce early star-forming sites. So dark matter variants are not automatically a rescue, they are a rebalancing of structure, and Webb is sensitive to the timing of that balance. The early universe is a race between collapse, cooling, and feedback, and dark matter sets the starting conditions. Yet there is a subtler possibility. Some dark matter physics could accelerate the collapse of rare peaks, even while suppressing small scales overall. If the distribution's extreme tail changes, a few exceptionally massive halos might appear earlier than expected. If rare massive halos become relatively more prominent early, the bright tail could fill faster. but this must match observed clustering and lensing. A model that produces too many rare peaks would leave fingerprints in the spatial distribution of galaxies and in the statistics of magnification. The third family of ideas modifies gravity. This is the most radical lever, because gravity governs both expansion and the growth of structure. Change gravity, and you change the rules of collapse, the depth of potentials, and the way light bends through the cosmic web. Modified gravity can change how perturbations grow without changing the background expansion in the same way. That separation is why it is tempting. In some frameworks, the universe can expand almost normally, while structures grow faster or slower than expected. A small change in the effective strength of gravity at early times could speed halo growth. It could make massive structures appear earlier than LCDM predicts. The visuals show overdensities deepening more quickly, as if gravity had a slightly stronger grip during the first few 100 million years. But the evidentiary bar is high. Gravity is tested in the solar system, in binary pulsars, and in the large-scale universe through lensing and clustering. Any modification must hide where we already tested it, often by screening mechanisms that suppress deviations in dense environments. Any modification must also reproduce the CMB anisotropies, which are sensitive to gravitational potentials. The CMB does not only measure the sound horizon, it also measures the early integrated SACs, Wolf effect and lensing of the CMB itself. Those effects depend on how potentials evolve over time. If gravity changes, potentials decay or deepen differently, and that alters large-angle temperature fluctuations and the smoothing of peaks by lensing. The CMB, in other words, is watching gravity as well as geometry. So modified gravity must be engineered carefully. It must change growth enough to help Webb, while leaving the CMB's pattern nearly untouched. That is possible in principle, but difficult in practice because multiple observables constrain the same underlying dynamics. The universe has too many independent ways to measure the same physics. Lensing maps how mass bends light, peculiar velocities map how mass pulls matter, and clustering maps how mass seeds structure. A successful modification must pass all three tests while still explaining the expansion history. The fourth family of ideas revisits inflation. Inflation sets the initial conditions, the spectrum of primordial fluctuations that later become galaxies. It is the origin story for the seeds that gravity later amplifies, and it is therefore a lever on how early structure can appear. LCDM usually assumes a nearly scale-invariant Gaussian spectrum with a specific amplitude. That spectrum is measured in the CMB with high precision. The tilt, the amplitude, and the absence of strong features are not casual assumptions. They are empirical statements based on the sky. But inflation is not a single model. Different inflation scenarios can tilt the spectrum at running, or introduce features at specific scales. A small feature at scales smaller than those best measured by the CMB could, in principle, change early halo abundances. If small-scale power were slightly enhanced, more early halos could form. That could increase the abundance of early galaxies without changing late-time expansion. The image becomes a power spectrum curve with a subtle bump, barely visible, yet consequential for rare objects. Yet the CMB constrains the spectrum on large scales, and large-scale structure constrains it on intermediate scales. Any feature must avoid those constraints. If the enhancement leaks to scales we have already mapped, it would distort clustering statistics and lensing in ways we would notice. Non-Gaussianity is another lever. If primordial fluctuations were slightly non-Gaussian, rare peaks could be more common than in a Gaussian field. In a Gaussian universe, extreme peaks are exponentially rare, so even a small change in the tail can matter. More rare peaks means more early massive halos, even if the average power spectrum stays similar. That could populate Webb's bright tail earlier. The visuals show a probability distribution with a subtly heavier tail, turning improbabilities into occasional realities. But non-Gaussianity is constrained by the CMB spectrum and by galaxy surveys. The allowed room is small, and the signatures are specific. A model that boosts rare peaks too much would also produce measurable correlations in the pattern of fluctuations. So inflation offers flexibility, but not freedom. It can adjust the odds of early structure, but it must still match the CMB's statistical fingerprints. The early universe may allow a tweak, yet it does not allow an untraceable rewrite. Across all these ideas, the theme repeats. Fixing Webb by changing cosmology means changing the timeline, the growth, or the initial conditions. But those three are entangled, and the entanglement is what makes this chapter feel like a puzzle box. Expansion affects growth, because faster expansion can dilute matter's ability to collapse. Growth affects reionization, because early stars and black holes ionize hydrogen and change the intergalactic medium. Reionization feeds back into the interpretation of early spectra, because it shapes which photons escape. This is why cosmology fights back. Every proposed adjustment must pass through a gauntlet of cross-checks that were built for other questions. The modern dataset is not one experiment, it is a network, and the network is designed to catch inconsistencies. Baryon acoustic oscillations measure the same sound horizon at later times. They tie early universe physics to the geometry of the low redshift universe. BO is the sound horizon's echo in the distribution of galaxies, a ruler stamped into the cosmic web. If early dark energy shrinks the sound horizon, BO distances shift. The model must then adjust other parameters to keep BAO and supernovae consistent. That adjustment can involve matter density, dark energy behavior, or curvature, and each has its own observational consequences. Large-scale structure measures the growth of matter fluctuations over time. Weak lensing and galaxy clustering trace how gravity assembled the cosmic web. These are not just pictures, they are statistical fields, and they constrain how quickly fluctuations grew from the CMB era to today. If we change growth to help early galaxies, we risk mismatching the observed amplitude of clustering today. The parameter S8 becomes part of the argument. It is a compact way of summarizing how lumpy the universe is on a characteristic scale, and it is measured in several independent ways. This creates another tension. Some solutions to the Hubble tension raise S8, worsening the so-called S8 tension in weak lensing surveys. The web tightens again, because a model that makes expansion fit better can make structure fit worse, so a fix can trade one disagreement for another. The universe does not allow a single knob to be turned without moving several needles. The narrator's cadence slows, emphasizing that these are not isolated puzzles, but linked constraints. Big Bang nucleosynthesis is a hard anchor. It fixes the baryon density and limits extra radiation or energy density in the first minutes. The early universe's nuclear reactions depended on temperature and expansion, and the resulting abundances are measured in ancient gas clouds. Add too much early energy and helium and deuterium yields shift. The observed abundances then become a veto, even if the CMB fit improves. It is a reminder that the first 3 minutes still speak, and they speak with surprising clarity. The CMB power spectrum is also unforgiving. The heights and positions of peaks encode baryon loading, matter radiation equality, and diffusion damping. The damping tail in particular is sensitive to how photons random walked through the plasma, smearing small-scale anisotropies. A model that changes early expansion must still reproduce those peak ratios. It must also reproduce the damping tail, which is sensitive to recombination physics. The visuals show the spectrum as a comb of peaks, where even small shifts are obvious to a trained eye. Even recombination itself can be questioned. If the ionization history differs slightly, the CMB inference of parameters can shift. A small change in how quickly electrons combined with protons can alter the visibility function, changing how sharply the CMB last scattering surface is defined. But recombination physics is based on atomic processes we understand well. It is not impossible to tweak, but it is not an easy hiding place. Any proposed change must remain consistent with laboratory physics and with the detailed polarization pattern of the CMB. So the story becomes a balance sheet. Webb's early galaxies add a new line item, and the Hubble tension adds another. The question is whether both line items point to the same missing ingredient, or whether they reflect different kinds of error. There is a seductive narrative where everything connects. A modified early expansion raises H0, changes the redshift time mapping, and helps early structure. It feels elegant, because it promises a single cause behind multiple anomalies, but the same narrative can fail under scrutiny. A higher H0 can make the universe younger, and a younger universe makes Webb's early galaxies harder. The elegance can collapse into contradiction if the timeline tightens faster than structure can plausibly grow. So the goal is not simply to raise H0, the goal is to change the expansion history in a way that fits all clocks at once. That means respecting how different datasets measure time. Some measure it through geometry, others through growth, and others through relic abundances. That means distinguishing between the age of the universe today and the time available at high redshift. Those are related, but not identical. A model can adjust early expansion and late expansion differently, changing inferred H0 while keeping the total age closer to the standard value. A model can, in principle, keep the age similar while shifting the inferred H0. That is why early dark energy is framed as a temporary episode. It changes the early ruler without permanently rewriting the late-time universe, at least in its simplest versions. But even temporary episodes leave traces. They change the timing of matter-radiation equality, the growth of perturbations, and the onset of structure. They can also alter how quickly the first stars ignite, which changes the ultraviolet background and the reionization timeline. For Webb, the key is the cosmic timeline in the first few 100 million years. That timeline is computed from the expansion history, not read directly. The narrator returns to the idea that the early universe is not dated by a label, but by a model-dependent conversion. So the phrase "older than the Big Bang" returns in a new form. Webb is not finding pre-Big Bang objects. It is testing our translation from redshift to age, and it is testing it at the most demanding end of the scale. If the translation is wrong, then early galaxies only look impossible. If the translation is right, then early galaxies demand extreme astrophysics or new physics. The tension is productive, because it forces us to ask which assumptions are doing the most work. The mystery is that both options remain open. The data are good enough to create tension, yet not complete enough to force a single resolution. Photometric candidates can mimic high redshift, stellar populations can masquerade as older or heavier, and lensing can quietly amplify. So we reframe the central question at maximum stakes. Are Webb's galaxies exposing a measurement artifact, an astrophysical sprint, or a missing cosmological chapter? The visuals split into three paths, each with its own icons, spectra, starbursts, and equations. A missing chapter would not erase the Big Bang. It would revise the early universe script that connects the CMB to the first galaxies. The revision would be constrained, not free, because the CMB is a high-precision record that any new story must still honour. It would have to preserve the CMB's precision while changing what the CMB implies. That is a delicate requirement. It asks for a model that changes derived parameters without ruining the fit to the spectrum itself. This is the paradox of modern cosmology. The model is successful enough to be hard to change, yet precise enough that small cracks matter. In earlier eras, uncertainties could absorb anomalies, but now anomalies stand out as structured disagreements, so we do not end with a new theory. We end with a decision tree, and with the test that can prune it. The narrator's voice becomes procedural, because the next step is not imagination but measurement. The deciding evidence will be multi-pronged. It will come from better spectroscopy of the highest redshift candidates, to lock down distances and lines. Spectra can reveal whether a break is truly Lyman alpha absorption at high redshift, or a dust-reddened feature at lower redshift. It will come from wider area JWST surveys, to reduce cosmic variance and measure number densities with real statistical power. A few deep fields can be misleading, because rare objects cluster, and a small patch of sky can land on an unusually rich region. It will come from gravitational lensing maps of foreground structure, to quantify magnification bias and remove hidden boosts. Weak lensing shear fields and galaxy mass maps can identify where magnification is likely and where it is not. It will come from improved stellar population models, including nebula emission, dust physics, and flexible star formation histories. Nebula lines can inflate broadband fluxes, dust can redden without aging, and bursty histories can mimic high mass-to-light ratios. It will come from independent H0 measurements, including time delay lenses, megamasers, and gravitational wave standard sirens. Each method has different systematics. An agreement among them would strengthen the case that the tension is physical. Time delay lenses use the fact that light takes different paths around a massive galaxy, arriving at different times. The delays depend on geometry and the gravitational potential, and with careful modelling they provide a direct handle on H0. Megamasers, in contrast, are geometric. Water masers orbiting supermassive black holes trace Keplerian rotation, letting us measure distances through angular size and velocity. They are rare, but when they appear, they offer a clean rung on the ladder. Standard sirens add a different kind of ruler. Gravitational waves encode an absolute luminosity distance in their amplitude, and an electromagnetic counterpart can provide redshift. As detections accumulate, the method becomes less about one event and more about a population. It will come from Bayo and supernova refinements, to test expansion history without relying on the CMB alone. Together they map distances across cosmic time, and they can reveal whether the expansion curve has subtle departures from LCDM's expectations. It will come from large-scale structure and weak lensing to test whether growth histories match any proposed early universe modification. Growth is the other half of the story, because changing expansion without changing growth is difficult, and changing growth without leaving traces is harder. And it will come from CMB polarization and lensing reconstructions, which can tighten constraints on early energy components and gravity. Polarization sharpens our view of recombination, while CMB lensing maps the integrated mass distribution, linking early physics to late structure. This is the transition from speculation to method. The universe will not be argued into a new model, it will be measured into one. The visual shift from dramatic cosmic vistas to the patient work of surveys, pipelines, calibration stars, and cross-correlation matrices. In the meantime, the tone stays deliberately uncertain. Every new ingredient can rescue one dataset while endangering another. That uncertainty is not weakness. It is the honest posture of a field that has learned how easily confidence can outrun evidence. Cosmology is not collapsing. It is being audited under harsher light, and Webb is part of that light. The telescope's sensitivity does not just reveal distant galaxies, it reveals the assumptions embedded in our conversions, our priors, and our models. The climax is not a single revelation. It is the realization that our cosmic timeline is a derived object, and derived objects can be revised. When the derivation is tested at the edge of the observable universe, even small mismatches can look like paradoxes. What Webb may have found is not something older than the Big Bang. It may have found that the early universe had an extra chapter we have not read, or it may have found that our reading is correct, and the early galaxies were simply more efficient than we imagined. Next, we move from the menu of possibilities to the verdict process. We follow the observations that will decide what is real and what only looked real. The screen fades from the deep field to a checklist of upcoming surveys as the mystery becomes an experiment. The mystery ends the way science always ends it, quietly and on paper. Not with a proclamation, but with a verdict built from tests, cross-checks, and the stubborn arithmetic of uncertainty. We return to the hook with precision, because precision is the only antidote to cosmic temptation. Webb did not see beyond the Big Bang, because beyond is not in our light cone, and no telescope can collect photons that never had time to arrive. That boundary is not philosophical. It is geometric. Space expands, light travels at a finite speed, and the observable universe is defined by causal contact, an edge drawn by time itself. What Webb did was push the timeline to its hardest edge, where interpretation becomes fragile and every assumption matters. It forced us to ask whether early galaxies formed faster than expected, or whether we misread what their colours were trying to say. In the earliest releases, a few red points in deep fields looked almost too bright, too heavy, too mature. The images were gorgeous, tiny smudges suspended in black. But the real drama was mathematical, hidden in how we translate flux into history. This is the transition from speculation to method. The question becomes which measurements can survive every alternative explanation, including the ones we would rather not entertain. Near-term JWST priorities are straightforward and unforgiving, because the first step is always to confirm distance. Spectroscopy must replace photometric guesses for the highest redshift candidates, especially when a single filter can mislead. Photometry is fast and it is powerful, but it is also indirect. A steep drop in brightness can be the Lyman break at extreme redshift, yet dust reddening or strong emission lines can imitate that same silhouette. Near-spec programs target the break and the lines together, turning a colour-based hunch into a physical measurement. A confirmed redshift means multiple features agree, not one ambiguous drop in flux that could be explained three ways. The key is pattern recognition in wavelength space. Hydrogen absorption, oxygen lines, and the spacing between features act like a barcode. If the bars align, the distance is real. If the redshift is real, the next task is mass, because mass is where the claim becomes provocative. Improved stellar mass estimates require separating continuum light from mission line boosts, which can inflate broadband flux by factors that matter. In early galaxies, nebular emission can be extreme, because hot young stars flood their surroundings with ultraviolet photons. That radiation excites gas, and the gas answers back with bright lines that land inside Webb's filters. Spectra measure equivalent widths directly, and that is more than a technical detail. It turns a suspicious broadband bump into a quantified correction, with uncertainties that propagate honestly through the mass estimate. When the correction is applied, some galaxies shrink in inferred mass, and the tension relaxes. Others remain stubbornly luminous even after the accounting, and those are the objects that keep the question alive. Metallicity and dust are the next pressure points, because they are clocks as well as ingredients. Line ratios and continuum slopes constrain enrichment, attenuation laws, and the physical state of ionized gas, which together reveal how many stellar generations have already lived. Metals are forged in stars and dispersed by winds and supernovae, so early metal lines imply rapid cycling. Dust is even more demanding, because it requires both heavy elements and pathways to assemble grains in harsh radiation fields. If metals and dust appear early, they must be consistent with rapid star formation and supernova yields, not just with a convenient fit. If they do not appear, their maturity claims weaken, and the galaxies look more like brief, intense flashes. JWST also tests star formation histories, not just snapshots, and that is where the story becomes temporal. Multiple spectral features can distinguish a short burst from a long, steady build, even when the images alone look identical. Balmer breaks, nebular continua, and rest optical lines constrain ages, because different stellar populations leave different fingerprints. They also reveal whether the inferred mass-to-light ratio is plausible at that epoch, given the universe's limited time. A strong Balmer break suggests older stars, yet at very high redshift the cosmic clock is brutal. The question becomes almost visceral. How do you grow a seemingly mature population in only a few 100 million years? AGN indicators are part of the same checklist because black holes can counterfeit starlight. High ionization lines, broad components, and compact continua can expose accretion, masquerading as a massive stellar population. An active nucleus can heat dust, harden spectra, and add a central glow that looks like extra stars. If an AGN contributes significantly, stellar masses drop, but black hole growth then becomes part of the early timeline that models must explain. The next wave is not only deeper, it is wider, because population claims live or die on statistics. A few spectacular objects can be a fluke, but a persistent excess across the sky becomes a structural challenge. Early deep fields were narrow windows, chosen for low foreground dust and clean viewing. Narrow windows suffer cosmic variance, where one overdense line of sight can look like a universal rule, simply because the universe is clumpy. In visual terms, the deep field is a keyhole view into a vast cathedral. If the keyhole happens to point toward a crowded balcony, the whole building can seem full, even when most aisles are empty. Wider JWST surveys reduce that variance by sampling independent patches of sky, each with its own large-scale structure. They measure the bright end of the luminosity function across regions that do not share the same cosmic neighborhood. The luminosity function is not just a curve, it is a census of rarity. The bright tail is where anomalies shout, because extreme objects should be exponentially uncommon in standard growth histories. If the abundance of bright galaxies falls with area, the crisis softens into selection and geography, and the universe returns to statistical normalcy. If it persists, the anomaly becomes harder to dismiss, because the sky itself is voting. Population statistics also sharpen completeness and contamination, which are the silent enemies of early claims. Selection functions must be measured, not assumed, especially near detection thresholds where noise and bias can conspire. A robust census requires consistent pipelines, uniform priors, and transparent error budgets, because every catalogue is also a model. Otherwise, the sample becomes a mirror of our assumptions, and the apparent crisis is self-assembled. Gravitational lensing is a second statistical trap, because it can brighten galaxies without announcing itself. Modest magnification can inflate the bright tail without obvious arcs or dramatic distortions, especially when foreground structure is subtle. Lensing is the universe's own optical trick. Mass bends space and space bends light. A galaxy can look intrinsically powerful when it's merely well positioned behind a foreground concentration of dark matter, so lensing corrections must be systematic, not a post hoc patch applied only to suspicious cases. Foreground mass maps and shear fields quantify magnification bias, across each survey footprint, turning a qualitative worry into a numerical correction. If bright candidates cluster behind foreground structure, lensing is implicated and the bright tail may deflate. If they do not, lensing becomes a limited correction, not a rescue, and the galaxies keep their improbable brightness. This is where cross-observatory synergy becomes decisive, because no single instrument measures every relevant piece. Webb measures starlight and lines, but other instruments measure the missing components that starlight alone cannot guarantee. ALMA tests cold dust and gas directly, and it does so in wavelengths where dust stops hiding. If dust is invoked to redden spectra, ALMA should see corresponding far-infrared emission, or it should set limits that make heavy dust implausible. ALMA also measures C2 and other traces of the interstellar medium, which can be luminous even when stars are faint. Those lines anchor dynamics, gas mass, and sometimes redshift itself, providing an independent rung on the distance ladder. Dynamics matter because mass is not only light-based. Line widths and velocity gradients hint at gravitational potential, and they can reveal whether a galaxy's inferred stellar mass fits inside its own kinematics. Ground-based ELTs extend spectroscopy with raw collecting power, and they do it with a different set of systematics. They can target faint continua, resolve line profiles, and search for subtle AGN signatures that Webb may only suggest. ELTs also enable larger samples with repeatable setups, which is crucial when the debate shifts from a few objects to the shape of a distribution. Repetition is not glamorous, but it is how science turns wonder into reliability. The Roman Space Telescope changes the geometry of the problem because it trades some depth for enormous area. Roman will map wide-field infrared sky, building large early galaxy samples that Webb can then interrogate in detail. Roman will also deliver lensing maps at scale, turning magnification from a suspicion into a measured field. Those maps improve corrections and connect early galaxies to the foreground mass web, which is itself part of the cosmic story. Other observatories add independent constraints, and independence is the point. X-ray and radio facilities can test obscured accretion, while future CMB and lensing surveys tighten growth histories, limiting how freely models can bend. Together, these datasets create cross-checks that are hard to fake, even unintentionally. A galaxy cannot be simultaneously dust-rich, dust-dark, and line-dominated without leaving traces in at least one band. So what counts as decisive evidence for a real crisis? First, a large sample of spectroscopically confirmed redshifts at the highest claimed values, with multiple lines or breaks agreeing in each case. Second, masses that remain high after line removal, AGN subtraction, and lensing correction, because each correction targets a different illusion. The mass must be robust under reasonable stellar population assumptions, not only under the most extreme fits. Third, number densities that stay high across wide areas, because rarity is the heart of the claim. The bright tail must remain too common even when cosmic variance is minimized, and when selection effects are explicitly modeled. Fourth, star formation histories that demand long build-up times, not just intense recent bursts. If spectra imply older stellar populations than the cosmic time available, the tension becomes structural, not merely a calibration dispute. Fifth, metallicity and dust that require multiple generations of stars because enrichment is cumulative. Enrichment must be consistent with yields, feedback, and the global reionization budget, which sets limits on how many photons early stars can plausibly produce. If all 5 discriminants align, too massive too early becomes unavoidable, and the debate changes character. At that point, the anomaly is not one galaxy, but a coherent pattern, repeated across fields and confirmed by independent instruments. Then cosmology responds, but it cannot respond freely, because the early universe is already tightly constrained. Any change must satisfy the CMB acoustic peaks and Big Bang nucleosynthesis constraints, which are among the most precise measurements in all of science. There is historical weight here, because the standard model earned its status through survival. The CMB was predicted before it was discovered, nucleosynthesis matched primordial abundances, and large-scale structure grew in simulations that echoed what surveys later mapped. One response is parameter shifts within the standard framework, which is the least dramatic path. Small changes in matter density, baryon fraction, or the primordial spectrum can move predictions modestly, and sometimes modestly is enough. Another response adds new components, like early dark energy, which briefly alters expansion before fading. It can change early growth and the sound horizon, but it must not break Bayer and lensing, which act like independent referees. Dark matter changes are also considered, but they cut both ways and the direction is not guaranteed. Many variants suppress small-scale structure, which can make early galaxies harder, not easier, unless the model also changes how efficiently gas cools and collapses. Inflation revisions are a subtler lever, because they reshape the initial conditions rather than the later rules. A small-scale power feature or mild non-Gaussianity could boost rare peaks, but CMB statistics limit the allowed room, and the limits are unforgiving. Modified gravity is the most radical option, because it touches the engine of growth itself. It must hide in local tests while changing early growth, and that is a narrow corridor of viability, lit by constraints on every side. The key is that new physics must solve multiple tensions at once, not merely decorate one anomaly. A fix that helps Webb while worsening the CMB or BBN is not a fix, it is a trade that the data will eventually reject. If the anomaly fades, the lesson is still profound, because it teaches humility about inference. It means our pipeline was the frontier, and Webb revealed where our priors were brittle, especially when data are sparse and the universe is young. If the anomaly persists, the lesson is also profound, because it changes the tempo of cosmic history. It means the early universe was more efficient, or more complex than our baseline story allowed, and that efficiency must be explained rather than assumed. Either way, the Big Bang is not a fragile myth, and it does not collapse under pressure from a handful of galaxies. It is a rigorously tested framework that has survived decades of independent cross-checks, from background radiation to elemental abundances. Yet Webb is expanding the frontier where that framework must be tested hardest, right where the first structures ignite. The first few 100 million years are where small assumptions become big conclusions, and where errors can masquerade as revolutions. So we end with the verdict horizon, not a final verdict, because science rarely offers finality. The origin story remains coherent, but it is not complete, and the incompleteness is where discovery lives. Scientific discovery thrives at the edge of contradiction, where the next measurement can either dissolve a mystery or deepen it. The universe's age and origins are best treated as a continuously tested map, and Webb is redrawing it in infrared light. As the spectra accumulate and the surveys widen, an old question returns in a new voice. Are we seeing the universe as it was, or as our methods allow it to appear? And how do we tell the difference when the light is this ancient? Across these chapters, Webb's impossibly early galaxies change from a headline into a forensic case, built from faint infrared photons and careful subtraction. We followed how redshift becomes a clock only through a cosmological model, and how light becomes mass only through assumptions about dust, metals, nebular lines, black holes, and stellar populations. And we watched the standard timeline push back because the CMB, nucleosynthesis, BAO, and lensing form a chain set of constraints that cannot be rewritten casually. Webb's deep fields revealed candidates at Z10 and beyond that look bright, structured, and sometimes chemically mature, yet the real tension lives in the translation layer between observation and inference. Photometric redshifts can be fooled by emission line boosting and dust reddening. Lensing can magnify rare sources into seeming common ones, and bursty star formation can mimic large masses with short-lived brilliance. Still, even after demotions and revised fits, a stubborn subset keeps the question alive, shifting the mystery from a few outliers to population statistics and number densities. That is why the documentary kept returning to audits rather than declarations, because cosmology is not one dataset but a negotiated truce among many. If the early galaxies truly are too massive, then either early astrophysics was more efficient than our simulations allow, or our initial conditions produced more rare peaks, or the expansion history carried a subtle extra ingredient. Yet every new physics doorway, early dark energy, modified gravity, dark matter variance, inflationary features, must still pass through the narrow gate of the acoustic peaks, the primordial element abundances, and the growth of structure we already measure. So the story ends, for now, at a verdict horizon defined by the next round of discriminants. Spectroscopy must replace colour-based guesses, robust masses must survive corrections for lines, dust, and AGN. Wide area surveys must beat cosmic variance, star formation histories must fit inside the cosmic time available, and early metals and dust must balance the universe's energy and yield bookkeeping. If those 5 tests converge, we will know whether Webb uncovered a genuine crack in our timeline or merely exposed how easily our pipelines can manufacture ancient-looking galaxies from limited information. In the cold open, we asked whether Webb exposed a crack in the Big Bang timeline, or whether we are misreading the oldest light in the cosmos. The most honest answer is that Webb did not find something older than the Big Bang. It found something older than our confidence, forcing a high-stakes audit of how we turn light into history. If the anomaly fades under spectra and statistics, the Big Bang framework will look stronger, not weaker, because it survived a harsher interrogation than it was built for. But if the anomaly persists, then the first galaxies will become our most ancient witnesses, testifying not against a beginning, but against our incomplete account of how the beginning unfolded. Either way, Webb has done what the best instruments always do. It has moved the frontier from what we can see to what we can justify. The universe is not only stranger than we imagine, at its first dawn, it may be stranger than our methods allow us to admit. As new spectra and wider surveys arrive, follow the 5 decisive tests, because the next correction may be mundane, or it may rewrite the earliest chapter of cosmic history.